Okay, good morning, everyone. Thank you so much for those of you both who are at the San Juan College Henderson Fine Arts Center here, as well as our Zoom participants joining online. It's really great that we're able to have this hybrid style meeting to allow as many people to attend this year's 2022 Animas and San Juan Watersheds Conference. On behalf of the New Mexico Water Resources Research Institute, I'm really honored to be able to help host and put together this event. Yesterday, we were able to hear numerous wonderful presentations regarding watershed planning, policy, supply chains, plant science, and I'm really honored to share today's presentations with you all. We'll have a morning slate of presentations from the USGS and their collaborators on the works that they've been doing in the watershed. And with that, it's my pleasure to introduce our first presenter of the morning, giving two presentations here. Christina Ferguson is a hydrologist at the USGS New Mexico Water Science Center. Christina received her master's in geochemistry from the University of New Mexico in 2020. Her areas of research include geochemistry, karst hydrology, and sediment chemistry. Christina, it's an honor to have you here this morning. And I'll pull up your slides right there.
Yate bene. Good morning. So glad to see you all here today. Okay, so we're running slightly behind schedules and I talk really fast. So here we go. First, we're going to talk about the sediment chemistry collected from 3 reservoirs along the Animas and San Juan rivers here in the watershed. So just to orient ourselves, we all know where we are. Hopefully, you know where you are. Does this thing have a pointer? No. Okay, so we are looking at the Four Corners region. The black outline on the map on the right shows the outline of the San Juan watershed, the way that we look at it for our work at the USGS. Labeled on here, which turned out to be a little bit too small, we have Aztec Reservoir in a blue star. Can you see this pointer if I put it up there? No. Okay. Aztec Reservoir, Farmington Lake, and the San Juan Generating Station further down along the San Juan River. So we're looking at sediment chemistry, but why do we care about sediment chemistry? It's just dirt. It turns out that reservoirs along watersheds like these serve as storage for the sediment in the area. And that sediment can be a record of the materials that have come down the watershed through time. So we looked at 3 reservoirs. Aztec Reservoir number 1 and Farmington Lake are along the Animas River. And and which one was it? There it is. Okay. And the San Juan Generating Station raw water reservoir is fed by the San Juan River. I have to have 2 clickers. Okay. So the first location we're going to look at is the Aztec Reservoir number 1. It's located in the city of Aztec. Here, it is fed by the Animas River from 2 locations. It's directly pumped from the river, and it's also fed by a ditch that is diverted from the Animas River further upstream. Whoops, wrong one. So for this reservoir, it was drained prior to us going out and collecting the sediments. So you see here the locations 1, 2, 3, and 4 are where we collected sediments. What is shown on this map also are the input for the irrigation ditch, the input directly from the river, and the outtake where the water goes to be treated after it's been settled. This reservoir was built in 1947. The city of Aztec has relied on surface water from this reservoir since 1951. The reservoir was extended, the walls were built up in 1981 to make it deeper. I have too many clickers. which one does what. The second reservoir we're going to look at is Farmington Lake. It's a little bit further downstream, but also sourced by the Animas River. It also has two intakes. One is the, whoops, wrong button. One is the farmer's ditch input, which is right here, which is a irrigation ditch diverted from the Animas near Cedar Hill. And the other one is water pumped directly from the Animas down here. Before the water enters this reservoir, it goes through some serpentine settling ponds to get a lot of the sediment out. This lake is 198 acres. The Animas intake wasn't added until 1982. This lake gets about 21 centimeters of precipitation per year, but the evaporation is 97 centimeters per year. So we're working in the negative for this lake. The maximum depth of this lake is about 90 feet. And the dam was constructed, the dam is down here at the bottom. It was constructed in the early 1960s and no dredging of any sediment has ever been done. So the sediment in this lake is a complete record. Also, the thing to note about Farmington Lake is that it is unlined. Aztec Reservoir is lined, but this one is unlined. The last reservoir we're going to look at is the San Juan Generating Station Raw Water Reservoir, which is located along the San Juan River near water flow. And its intake from the San Juan is down here. There's a diversion right here that goes up and pumps water into the reservoir. And that's just a holding reservoir for raw water that's used to cool the towers. So we collected cores from this one in 4 places also. Here you see the input from the San Juan River from the pump, and here's the overflow where if the reservoir needs to be drained, it can be drained that way. There's also an arroyo that drains directly into here if it ever has water in it, which as we know is not very often. The reservoir was built in 1971, and in 1981, the dam was raised to increase the retention volume. So for Aztec Reservoir, we were there when it was dry. So, well, I say we, I wasn't there, but Jeb and Tyson and Johanna dug trenches and collected sediment at centimeter resolution, I think 10 centimeters. For Farmington Lake and SJ and the San Juan Generating Station Reservoir, we used the coring boat from the Oklahoma, Texas Water Science Center, operated by Chris Vaughn and Craig Wise. That core is gravity driven, so we basically just drop it off the boat and slam it into the bottom of the reservoir and collect some sediments. So for some of the results, the Aztec Reservoir sediments, we kept a record encased here in resin of 3 of the trenches. The other thing that we did with Aztec Reservoir was look at the 137 cesium dates to try to understand the ages of these sediments. So the bottom of the core is 1947. We know that because that's when the reservoir was built and it's lined. So we're able to see the bentonite layer. Then using the cesium dates, we can find the 1963 age and then some fancy calculations by Jeb, and we get the estimated ages at depth based on sedimentation and compaction. So for Farmington Lake, we have no cesium dating because it's not old enough. If we did cesium, we didn't have anything beyond the 1963 spike to see the spike in the cesium, so we didn't do it. So we did this one based on sediments, compaction, settling rates, and the known age of the bottom of the core and the top of the core. We didn't do this with the San Juan Generating Station Reservoir sediments. That was outside the scope of that project. But we did do chemistry on all of these sediments because chemistry matters. So the first thing I'm going to show here is the results for the major elements and 3 of the core and 1 core from each reservoir. And we're looking at just the longest core for each reservoir to have the longest record. So for the next few slides, it's always going to be this way: Aztec Reservoir, Farmington Lake, and San Juan Generating Station. Concentrations are along the x-axis and depths are along the y. So for the major elements, we see what we expect to see. Everything is pretty stable. Aluminum is the highest concentration in all of the cores, followed by iron, which is what we would expect in this reservoir. So for the next one, we're going to look at arsenic in each of these reservoirs. And for this one only, the scales on the bottom are all the same for each trench. The blue line shows the average concentration in soils of arsenic, and the orange line shows the average concentration in urban soils. And as you can see, the only place where the arsenic is elevated relative to the average concentration in urban soils is at the bottom of Aztec Reservoir Trench number 1. Moving on to copper, same thing, concentrations are along the x-axis, but in this case, they have different scales. As you can see that the Aztec Reservoir scale goes up to 1,750 milligrams per kilogram. So that makes this spike here at the bottom incredibly enriched relative to the rest of the cores. You can see that the range here on the bottom on this Farmington Lake core only goes up to 120. So that spike, while it looks good, is not, it wouldn't even show up at this scale. On this graph, we also have the average concentration of copper in crust labeled in the purple line. So these sediments here in the Farmington Lake Reservoir are almost all elevated relative to that concentration. But in the San Juan Generating Station Reservoir, they're all low relative to that concentration. For the uranium, same thing, the scales on the bottom are all very different. The average concentration of uranium in the crust is about 3 parts per million. And so that's shown here in the purple line. I don't have information for the average concentration of uranium in soils or urban soils. So Johanna, we should do that. And note the scales are very different between even these, the Farmington Lake and the San Juan Generating Station Reservoir. This one, the San Juan Generating Station Reservoir it starts above the concentration, the average concentration in the crust. So all of those samples in the reservoir, the San Juan Generating Station Reservoir, are elevated relative to the average concentration in crust. So for the last one that we're going to compare, we're going to look at vanadium. And again, we see the same trend at the Aztec Reservoir, trench number 1, where all of the concentrations are elevated at the bottom of the core. The Farmington Lake core again has the Farmington Lake and the San Juan Generating Station Reservoir have the same scale, but they're different than the one for the Aztec Reservoir to show the variation. Okay. Also for 2 of the reservoirs, we went to UNM and loaded up some sediments on the scanning electron microscope. If you guys saw Rachel's poster yesterday, there were some other pictures from a different project for that. And what we found with Aztec Reservoir and Farmington Lake were some interesting, but not entirely unexpected little dudes. We have iron and aluminum oxide with some arsenic and chromium in 3 out of 4 of these spots, and one with an iron oxide silica with arsenic and chromium. We found these pretty much throughout all of the samples. One thing that I wanted to show because it's cool is this framboidal pyrite that we found in Farmington Lake. And we didn't see that in any of the other ones, just that one sample. We also, while we had the SEM out, we looked at diatoms in the samples. So again, we only did this for Aztec Reservoir and Farmington Lake. So here's an example of one of the diatoms from the Aztec Reservoir, and I apologize because I don't know what he's called, but there he is. And then same thing with Farmington Lake. This one has a whole bunch of little pieces of diatoms in it, but the most striking is this boat looking one right here. So I wanted to show that because it's cool. Okay, so in conclusion, Aztec Reservoir, number 1, is the only place that has sediments that predate the Clean Water Act of 1972. Again, that reservoir was built in 1947. So we see effects from upstream mining in that reservoir recorded in the sediments. Arsenic, copper, uranium, and vanadium all spike at the base of Aztec Reservoir. And that's that record that I mentioned about upstream mining. Farmington Lake sediment chemistry is likely affected by groundwater because it's unlined. And the lake itself sits in the Nacimiento Formation and in the Quaternary alluvium. Most of the concentrations of copper in the Farmington Lake core are elevated relative to the average concentrations of copper in the crust soils and urban soils. And most uranium concentrations in the core are elevated relative to crustal averages. For the San Juan Generating Station, the sediments do not have elevated concentrations of arsenic or copper, but the uranium concentrations are all above crustal average. And all 3 reservoirs show vanadium concentrations that are above crustal average, and most sediment samples have vanadium concentrations above that in soils and urban soils. And I went quickly, the end. You have any questions? Yes, sir.
The uranium and the vanadium process is nearly directly into the river for years. Are you aware of take that factor?
Yes, we did kind of a comprehensive history of the bad things that the mines did upstream in the Silverton Reservoir when we did the Aztec work. So we kind of have a history in there, so that mill is one of the mills that we definitely included.
And just a reminder, if you want to ask some questions, we have a wireless mic today. So just raise your hand and my colleague Anik will come over to you with the wireless mic.
Yes, sir.
So what do you do with this and what does it indicate? Like, is that deep coming out? Do anything?
Yes, actually, that's why we did the work, was to find out if the sediments were okay to be dredged and removed from the reservoir to increase storage. And so I didn't show the T-clip concentrations, but these sediments are all underneath the T-clip concentrations for, I think, everything that we looked at.
Underneath the what?
The T-clip, the toxicity characteristics, leaching procedure.
So you get that out, the water's gonna be cleaner.
It just increases storage. So if you scoop the sediments out of the bottom, you could put more water in. And then the sediments have to go somewhere, so they have to be below these standards so that if they sit there and get rained on, they're not leaching bad things. Okay, if that's it, I'll go to the next one, maybe. Let's see. All right, so compilation of the Lee Acres Giant Bloomfield Refinery database. So we are looking at the Lee Acres landfill. This is north of 64, kind of in between Farmington and Bloomfield. It's about 6 miles east of Farmington. It's adjacent to an unnamed arroyo, which is difficult to see at this scale, but there it is. It's north of the former Giant Bloomfield refinery, and the landfill covers approximately half a square mile. For the geology of the Lee Acres landfill, it's within the San Juan structural basin. The quaternary alluvium in the area is 20 to 60 feet thick, depending on where you are, and that consists of clay, sands, gravels, and cobbles. Underlying the alluvium is the tertiary Nacimiento Formation, and this formation has interbedded clay shale and some sandstones. So for the landfill itself, some of the background of the site, this landfill is on BLM managed by the BLM. When it was operated in 1962 to 86. In 1985, one of the liquid waste lagoons shown here in Peak breached and dumped all kinds of stuff into the arroyo. It caused dizziness and faintness to personnel on site, and they reported an hydrogen sulfide smell. In 1990, it was placed on the national priorities list for the presence of heavy metals and volatile organic compounds in the water. So since that, there has been a lot of work done on this site. The most recent record of decision by the EPA was in 2004. And so that record of decision laid out the things that were going to be done to remediate the site. The first thing that was done was this landfill cap installation, which you can see in these two dated aerial images. There's no landfill cap here, and here it is here. So that was completed in April of 2005. There was surface water runoff controls instituted, institutional controls, and monitored natural attenuation. So since this time, the only constituent of concern that remains is the dissolved manganese. All the rest of these things have been below detection for some time now. So a little bit on Giant Bloomfield Refinery, which is just south of the landfill. It was owned by Giant Industries and operated as a crude oil refinery from 1973 to 82. But in 1982, they changed operations at the site and it became just a dispatching and maintenance headquarters. In 1988, Giant Industries began remediating the site because of several historic releases of diesel, fuel, crude oil, and gasoline. So some motivation behind putting together this giant database. The landfill and refinery each have extensive groundwater monitoring histories, but the data were scattered across the web, all publicly available, but in so many different places in so many different forms. Also, several of the GBR wells up gradient of the refinery fuel release sites have poor water quality, and Lee Acres is frequently cited in GBR reports as a source of this contamination. That's strange. Okay. So the database was compiled by a team of hydrologists and student hydrologists from the USGS New Mexico Water Science Center. We compiled data from our water system, NWIS, from GBR monitoring reports, which are all PDFs and have to pull the data manually. And believe me, I'm so glad that somebody else was able to do that. From this remedial investigation that was conducted in the 90s, we pulled all of the water chemistry data from there and one New Mexico Environment Department water quality report. So LAGBIRD is a giant database. It's access-based. It contains over 5,000 groundwater elevations and 2,000 water quality records from 134 sampling locations. Now, all of those are not still existing at the sites. So when we look at this data now, we are just focusing on the wells that we monitor regularly. So for this work, we've gathered daily precipitation and temperature data from 28 stations in the Bloomfield and Farmington area in order to calculate evapotranspiration and then water balance for the region. We also downloaded precipitation chemistry data from the National Atmospheric Deposition Program for this period of time. To compare with the water chemistry that we see at the site. And for this work, because the data are from disparate sources and everybody does things differently, we've plotted filtered and unfiltered major ion water chemistry together, just to simplify. So at the site, we have 3 different aquifers as classified by the remedial investigation that was done in 1995. So we show a shallow alluvial aquifer. This is where the screen intercepts the water table. We have a deep alluvial aquifer where the screen sits at the bottom of the alluvium but doesn't cross into the bedrock, and then a bedrock aquifer. That's the nacimiento. So water levels have changed, which I know you guys would think, what? Water's changing? No way, but it does. Right. So some of the classifications of these wells have changed since they were classified and drilled back in the day. So the most notable of these changes is BLM 39. And BLM 39 is used as the up gradient background well for concentrations in the shallow alluvial aquifer. However, according to the classifications of the RI, it is no longer in the shallow alluvial aquifer and hasn't actually been in the shallow alluvial aquifer for some time. So we're going to move on to some results. We're going to look at general groundwater chemistry for all wells using all available data for this period of record, which is basically 1981 to 2020. We're going to look at precipitation dominated versus evaporation dominated water. We're going to see some Piper diagrams, some time series plots. We're going to look at sodium versus chloride. We're also going to look at the groundwater elevation, precipitation and water budget for the region and compare that to the manganese and chloride concentrations in the focus set of wells. So the very first thing we're going to look at is precipitation dominated versus evaporation dominated waters. And on the bottom, the x-axis, we have the sodium over sodium plus calcite and the chlorine over chlorine plus bicarb. And total dissolved solids is plotted along the y-axis. So some symbolization conventions that will follow through the whole thing. Shallow alluvial aquifers, all that those symbols will be circles. Deep alluvial and alluvial aquifers will have a triangle symbol. And shallow alluvial and bedrock aquifers will have a square. And here are all of the wells that we're going to look at. They're shown here on the map. Okay. I'll just start. The sample date, the older samples are more transparent and the newer samples will be more opaque. So those will show up better on the graph than the older ones. Our end member data include the liquid waste lagoon, which is symbolized by an X, precipitation in the region, which is a plus. And then we have two other kind of background wells, BLM 16 and BLM 40, which are going to be shown with an open square and a closed square. So for these graphs, anything above this kind of middle line, those water samples are dominated by evaporation. If they're below this box, they're dominated by precipitation, and in between, they're dominated by water-rock interaction. So the very first thing we're going to put on is precipitation, and yay, it falls in the precipitation area. That's so good. Yay. So the next thing we're going to put on is the liquid waste lagoon. So you can see that they're pretty elevated relative to the precipitation. Okay. Next thing we're going to see are BLM 16 and BLM 40, and they're also at the top dominated by evaporation. And then we're going to plop all of the other wells on because they all kind of plot in the same area, dominated by evaporation, which is not a surprise in the desert. Okay. Moving on to Piper diagrams, same symbolization, same colors, same end member symbolization. Okay. And the Piper diagram kind of shows us the water types. So the first thing we're going to put up is precipitation. And you can see that it kind of sits over here on the side and has, oh, where'd it go? Has kind of a range here and this top diamond shaped plot. The liquid waste lagoons, on the other hand, plot way down here. So these, you can see that these are kind of end member concentrations. BLM 16 and 40, BLM 39, BLM 45, BLM 60, and we're going down gradient here. We're starting from up here and moving down as I put these wells on. The next one is GBR 50, GBR 48, GBR 17. And we're just going to plop these on here because they're all kind of in the same place. Whoops, too far. So that tells us that all these water types are very similar and they lie somewhere on the mixing line between precipitation and the lagoons. So we're going to look at the manganese concentration over time for all of the wells. And shown here, the purple line is the date that the landfill capillary boundary was installed. And At the bottom, very small because the scale is big, are the Lee Acres landfill remediation level of 346 micrograms per liter. And the EPA secondary MCL for manganese is 50 micrograms per liter. But because of the scale, they're very small, tucked up against the x-axis. So the manganese range for BLM 16 and 40 is somewhere between 14 and 33 micrograms per liter. So we can't really show it at the scale. But we do show, here's BLM 39, BLM 40, BLM 60, GBR 50, GBR 48. And again, I'm just going to kind of plop these on here. This is one of the bad boys, BLM 77. You can see he has this, he's the reason this graph is so, the scale is so big because of this spike here. Plop some more on. And so what this shows us is that the concentration of manganese over time is very variable, right? We have a lot of concentrations that are very, very low and some that are very high, and they don't seem to have like any trend. They don't all rise together or all drop together. There's a lot of data. So next we're going to look at chloride concentration. Same thing. The purple line is the capillary boundary on the landfill. And the orange line on this one is the EPA secondary MCL for chlorine. And we're looking at chlorine because it's a good tracer for in groundwater. So the range of chlorine in precipitation is very, very low, less than 1 microgram per liter. The range of chloride concentrations at the liquid waste lagoons are off this graph. They range anywhere from 2,200 to 4,500 micrograms per liter, roughly, milligrams per liter. So they're not shown on this graph. The range of chlorine at BLM 16 and BLM 40 is between 10 and 26 milligrams per liter. So it's this dark gray line kind of at the bottom. Then we're going to start popping our wells on. Here's the BLM 39, 40, 60, GBR 50, GBR 48. And we'll just plop them on here. And you can see that for two of these GBR wells, 48 and 32, their chlorine concentrations look very different. And for this next one, BLM 62, his chlorine concentrations are kind of different. BLM 75, stepping through these, again, the concentrations of chloride are variable. They're not consistent from well to well. They don't behave in an expected manner. It's misbehaving groundwater. So that's what we're going to look at some more. We're going to look at sodium versus chloride in all of these wells. This 1-to-1 line is the halite dissolution line. If the samples fall right on that line, the sodium and chloride in the water is a result of dissolution of halite, which is table salt. If they fall above that line, there's some other source of chloride that we don't know about. If they fall to the left of that line, it's the chloride in the water as a result of cation exchange. If they fall to the right of that line and below, it's a silicate mineral weathering or cation exchange in the other direction. So I'm going to put this little thumbnail up to show that here is the range of the liquid waste lagoons and all of the other wells. So this big graph is just showing this small part of this little thumbnail graph. So we start putting on our wells. And we could start to see some patterns with these waters. Okay, so some of these wells, GBR 32, GBR 48, BLM 68, they have a different trend, right, than these wells down here. So with that in mind, we're going to start focusing now on just the wells that we sample regularly. So those wells are shown in the map to the right. These are the wells that we're going to focus on. The very first thing I'm showing here is groundwater elevation, the water budget, and precipitation. So remember, water budget is calculated by calculating the evapotranspiration for the area and then subtracting that from precipitation. So what's left over is the water that could possibly go into groundwater. On the bottom are the dates of the groundwater elevation, the groundwater elevations were collected, and the lines are color coded to the wells. So this black line is GBR 39. This light green line is BLM 77. The dark green line is BLM 62. The yellow line is GBR 48. And this pale blue line is BLM 80. So we start to notice some behaviors that are similar for some of these wells. They all kind of have a dippy-do here and then a rise in groundwater elevation following that. Dippy-do is a technical term, by the way. So now we're going to look at groundwater, groundwater elevation and manganese concentration at BLM 39. Again, dates are on the bottom. Groundwater elevation is shown here on this y-axis, and concentration of manganese is shown on this y-axis. The purple line is the date of the landfill cap installation. The green line is the cleanup level for Lee acres at 346 micrograms per liter, and the blue line is EPA's MCL for manganese. It's a secondary MCL at 50 micrograms per liter. So when we plot this next to groundwater elevation, we're looking to see if there's any changes in the manganese concentration that happen when groundwater elevation changes. And in this graph, about the only thing that we see is what kind of looks like a negative correlation. When we get this big spike in groundwater elevation, all the manganese concentrations seem to fall. They seem to crash. But before that, there's not really much correlation between groundwater elevation and manganese concentration. I forgot I put that on there. So again, the aquifer symbols here. So now we're going to look at the same well, but it's chloride concentrations in groundwater elevation. The secondary MCL for chloride is 250 milligrams per liter, and it's off this graph. It's way up here. So for this one, we see some correlation between groundwater elevation and chloride concentration. As elevation increases, so does chloride. As it drops, if you squint your eyes and tilt your head, you can see this line between these samples kind of follows the groundwater elevation line. So that's interesting. Let's see if anybody else does that. So now we're going to look at BLM 62, and he's highlighted here with the green box in this cluster of wells down here below the refinery. So for this one, first thing we're going to look at is manganese concentration. And we see that before the installation of the landfill cap, manganese concentrations at this well are all relatively low, and most of them are below the 346 micrograms per liter set by EPA. But after that cap, manganese starts misbehaving, and it seems to follow groundwater elevation. So when the groundwater elevation increases, so does the concentration of manganese. When it drops, so does manganese. But it's only after that landfill cap was installed. So for chloride concentrations at BLM 62, here is the secondary MCL for chloride, 250 milligrams per liter. And again, prior to the installation of that cap, chloride is all relatively low at this well. And then after that cap installation, chloride shoots up, but it doesn't seem to be related to groundwater elevation, unless maybe there's a sharp increase in groundwater elevation here and a sharp decrease in chloride immediately following that, but it rebounds quickly. Moving on to BLM 77, looking at the manganese concentration. And this is that misbehaving well that causes the axis to go crazy over here. But we can see that overall, most of the samples at BLM 77 are not crazy high like this one, and they don't seem to follow groundwater elevation changes. For chloride concentrations at BLM 77, it's a little bit backwards from the other ones. Prior to the install of the landfill cap, elevations were elevated at BLM 77 and they started falling. And then after, they kind of maintained their values and then slowly started climbing up. There is an increase at the same time as this increase in groundwater elevation that we see in a lot of the wells, but that's really the only correlation with elevation that we see. That's fun, correlation with elevation. Okay. So BLM 80 manganese concentrations. BLM 80 was installed after the cap was installed, so we don't have any data prior to the cap installation. But what we can see is that the concentrations of manganese in this well are all above, mostly above the cleanup level for the Acres landfill at 346 micrograms per liter. And again, there's maybe some small correlation with this rising groundwater elevation, but not really, not very good correlation. For chloride concentrations, again, installed after 2005. So all of these first samples are all low and steady until we get this big flush of water in and the chloride concentrations rise with groundwater level at that time. GBR 48, looking at the manganese concentration. And on this graph, we have both filtered and unfiltered data. Unfiltered data are the unfilled squares. And those are all kind of at a later date. And I apologize for this color, it's difficult to see. So prior to the installation of the landfill cap, the concentrations at GBR 48 were all relatively low, except for these ones at the beginning. And then after that, we start getting into the unfiltered data and they seem to have a slight increase, but not really related to groundwater elevation at this well. So now looking at the chloride concentrations, again, on this one, we have water samples where we don't know if they were filtered or not. So we have unfiltered data shown here with an open unfilled diamond, and then the other ones are unknown, and those are shown with a black outline on a filled diamond. So prior to the installation of the landfill cap, the concentrations of chloride at this well are all pretty high relative to the MCL. But after that, they seem to drop, but they don't follow groundwater elevation in any way. So looking at the manganese concentration at GBR 50, he doesn't seem to be all that affected by the landfill cap. Prior to that cap being installed, these manganese concentrations were already headed down. And then after that cap installation, these concentrations are all below the cleanup level for 346 micrograms per liter. For chloride concentration at GBR 50, again, we don't really see any correlation here between groundwater elevation and chloride concentration. There doesn't seem to be any effect from the landfill cap being installed. There is a spike in chloride concentration here, but we don't have any groundwater elevation data for that time. So we don't actually know if groundwater rose there or not at this well. That's the result of compiling other people's data. It doesn't always complete. So we do just a little bit of statistics here at the end, because I know you guys are still so riveted. So let me get some statistics at you. So the colors on these graphs are tied to the colors of the wells, and we're only looking at the wells in this cluster. So we're not looking up here at this background well or these wells outside the cluster, because to do correlations, you need more than one thing, and they need to be close together. And these are also correlated with the groundwater gradient and the groundwater gradient direction. So bold numbers like here are highly correlated and or significant. So for BLM 62, the bicarb is highly correlated with manganese concentrations, and it's a significant value because the p-value is less than 5. Okay. Oh, I forgot. On the top, these are all filtered concentrations, and on the bottom, they're unfiltered. That's why we have different wells. Okay. So really, we don't see a whole lot of correlation between any of these constituents and manganese concentration. We do have a minor correlation here with groundwater gradient magnitude. And I only mention it because it's sort of significant because its p-value is less than 5. And then the other one that has some correlation with groundwater gradient magnitude and direction is down here at GBR 49. And in this one, it's negatively correlated fairly well and positively correlated with direction. But overall, there's not that much correlation. That's enough statistics. Okay, so conclusions. Mixing with various end members, such as the bedrock aquifer or elements originating from the landfill, could be controlling the sodium and chloride chemistry at the well. Groundwater elevations in the selected well seem to be better correlated with water balance than precipitation, which makes sense because water balance is the amount of water that could actually reach the groundwater. Dissolved manganese concentrations and groundwater elevations are positively correlated at 62 and negative at 39. There's a spike in dissolved manganese concentration in December 2013, concurrent with the steep rise in groundwater elevation at BLM 62, 77, and 80. Unfortunately, GBR wells did not collect manganese data at the same date, so we can't tell if those are also behaved the same way. But after that date, the manganese concentrations for the total, that's the unfiltered, also increase concurrent with the groundwater elevation. Chloride concentrations at BLM 39 appear to be correlated with the groundwater elevation. At 62, these concentrations increased beginning in 2006, and a rise in groundwater elevation seen at the BLM wells in 2015 is concurrent with a decrease in chloride concentrations at 62 and a rise at 77 and 80. So that is kind of like a flushing event. Like there was a lot of chloride sitting here, groundwater elevations went up and flushed the chloride down gradient to these other wells. So for next steps on this, we are working right now on a scientific investigations report. The draft is expected to be in review at the beginning of FY23. So the result of all this work is we still don't really understand what's going on with the manganese. It's just a misbehaving little dude. So if we do a focused manganese study, this could include things like drilling sediment cores to do elemental analyses and mobility experiments to see if we can get that manganese to release. We could install new monitoring wells to monitor aquifers of interest. And one thing that would be really good is a new shallow alluvial aquifer upgrading of the site so we could actually get a background. And we've already started sampling for redox indicators like dissolved organic carbon, sulfide, ferrous, and ferric iron to establish redox conditions and to explore the possibility that potassium permanganate applied at the landfill lagoons could be a source of manganese concentration contamination. My goodness, I am so done. Thank you.
Any questions? Please raise your hand and my colleague Anik will pass the mic around.
Good morning, my name is Bonnie Fry, next year of geology.
Hi, buddy.
I was wondering on your P values, the well that had the ice spike on manganese, was that significant?
There's not enough samples. So that was the problem with the significance on a lot of these. While they might be correlated, they're not significant because there's only 2 samples. So it's difficult.
So it could possibly be an outlier.
It could be. Yeah. Yes, sir.
I was curious about the measurement of dissolved oxygen in your sample, whether you're doing it now or how long. This seems to me that there's a strong relationship between dissolved oxygen and
Yeah. I was hoping nobody would ask that. It's kind of embarrassing because we haven't been measuring it consistently. We've been collecting data from this site since the early 1990s, and the DO hasn't been collected consistently at all the wells. So it's difficult to to see that. We're doing it now consistently and have been for the past couple of years, but there's a large gap for the DO just wasn't collected. Same thing for GBR wells. They don't collect field parameters when they collect their samples, unfortunately.
We have one question from one of our Zoom participants. Colleen asks if there's any indication that the contaminated groundwater is reaching surface waters.
As far as what we're looking at, no. We haven't looked at any of the surface waters. That could be something that was included in the next step, but I'd have to ask Whitney, and she doesn't look very happy about that.
I was to be clear on the graphs. I noticed that the groundwater was measured in elevation above sea level. So I was wondering if kind of like the line for groundwater was going up, does that mean that the groundwater was closer to the surface?
Yes,
Okay.
yeah. It's
So the
shallower.
groundwater line is going up and it's closer to the surface and not the sea.
Yes. Yes.
Last.
Hi, so I know that's a pain of creating databases from ancient data. So it sounds like something you're continuing to maintain that data as an ongoing project?
No, I think once this database is compiled, it's going to be in stasis, but it's all of the data predating 2020. And after that, all of our data are publicly available in Animas. We just won't be compiling GBR's data anymore.
That was my question.
Yeah, but you can get that from the OCD website if you're really excited. Is that it? Awesome. Thanks, guys.
Thank you so much, Christina. All right. It's my pleasure to introduce our next presenter. Jeb Brown is a hydrologist with the USGS New Mexico Water Science Center. He earned his undergraduate degree in biology and his master's degree in water resources from the University of New Mexico. Jeb works on a variety of issues related to fate and transport of fluvial sediment. His research has focused on streams with high suspended sediment concentrations, developing innovative surrogate methods for monitoring sediment shifting in sand channels, and integrating biological and chemical studies with sediment transport. Let's see here. Oh, and just to note, if anybody would like to use a, I just realized we have a digital pointer available here. So let me try this. The pen and, okay, so we'll do a laser pointer. There we go. So you can just click and unclick that. And let me bring up, oh, laser pointer. Oh. Okay. And yep, so just click right there to activate it. If you really need to use this one.
Okay, great. Thanks, Mark. I appreciate that. Your tech help and your introduction. Thank you. It's a pleasure to be with you guys all today. It's an honor to be with so many people who care about this watershed, managers, scientists, local people who literally give their blood, sweat, and tears to this watershed, and your livelihood is in this area. And it's an honor to be able to do some science and work in this area. It's been an inspiring day yesterday, seeing all the presentations, and hope to add some content to that. So the project that I'm going to be presenting to you today is a project that we're working on in collaboration with the New Mexico Environment Department and funded through EPA funds through the WIN Act. And that was funds that were released following the Gold King mine spill. So we all know the context for these funds and for the work that we're doing here. I'd like to recognize the colleagues who are helping out with this project. So of course, Dr. Johanna Blake, Grady and Grady Ball and Justin Nichols are not at this conference, but they're a great asset to the project. And of course, our star technician, Brian Resin, who's here. responsible for a lot of the data collection. And there's other people who are also helping out on the project that I didn't include as co-authors on this. So the goal of this project is to provide temporally rich estimations of suspended sediment concentration and metals concentration. So when I say temporally rich, I mean data that are collected every 15 minutes. You might be familiar with these type of data when looking at a hydrograph that the USGS publishes. So a hydrograph is a temporally rich data set as compared to some of the other sampling efforts like Christina was just talking about. When we collect a discrete sample, that's a point in time, but we don't understand what's happening in between these different discrete sampling events. So the goal of this project is to provide a little more temporally rich data set to understand metals and sediment transport in the Animas River. A secondary goal to this project would be to provide near real-time estimations of suspended sediment concentration and metals concentration on NWIS web. That's a little bit more tricky to tease out. Actually, it's quite simple to make an estimate. It's a little more difficult to make an estimate that's meaningful. And so we'll go over some of the limitations to that. Just to remind ourselves where we are in this project. This is the Animas watershed outlined in black. And this star right here across the border is the Animas Cedar Hill gauge, the USGS stream gauge. And so we get kind of territorial in our federal agencies. So we're poaching over into the Colorado Water Science Center on this project, but it is actually a site operated by our office. So this is where the site is actually located. All the data collection that I'm going to be talking about today is occurring at this USGS stream gauge. So first I want to give a little example of what a surrogate measurement is. This is a measurement of one thing that is either easier or cheaper to do than it is to measure something else. And probably one of the better examples is looking at stream flow. We're fairly comfortable looking at discharge record. Here's an example of a USGS hydrograph. But when you see this figure on the web, when you're checking a discharge record to see if you want to go rafting that day or fly fishing, this is actually a surrogate measurement. These data are being collected every 15 minutes, but we're not actually measuring stream flow. We're actually measuring the stage of water. How high is the water in the river? On the left is a kind of a standard USGS stream gauge. So we're collecting that data. The stage data is being transmitted, and then it's ran through a stage discharge rating. And that rating is developed by field technicians going out in the field and physically measuring the cross section of the channel and the velocity, and then computing a discharge for that stage value on their site visit. So a number of those being done over the years builds up to a statistical regression that is called a rating. So that's the rating that we use to give a value in real time of stage of discharge. So this is an example of a surrogate measurement we're seeing all the time. So in this study, we're going to use a couple of instruments as surrogate measurements for suspended sediment and for metals. One of the instruments that we're going to be using, that we are currently using, is turbidity. And turbidity is light passing out through a sample of water at an angle to a sensor, and that sensor picks up the amount of refraction of that light as it hits particles in the water. So the light passes out, gets scattered around, and the sensor says there's a lot of something or there's a little of something. So we have, at this site, we have 3 turbidity sensors installed. One is the traditional sensor that's been installed since the Gold King mine monitoring came online. We have 2 other instruments installed, this Analyte NEP 5000, which generally does a better job at the upper end of turbidity values. It can record higher values of turbidity. And then this sensor down here on the bottom, which is a Turner turbidity sensor. They're a company that's paired with the hydroacoustic company that I'm going to talk about on the next slide. And so they kind of come as a package deal and work well together. So we're kind of doubling down on the ability to collect data very well with this instrument here, but at higher concentrations with this instrument here because the Animas River can be quite turbid at times, and this instrument would be overtopped with its value. Values would be recorded above its capability. So here's a record from last month at the site of what turbidity looks like. It's an example of what turbidity data are being collected. On the right-hand side is a USGS publication. It's a techniques and methods series. These are robust documents that talk about the procedure for how we do something, and it's well documented, and other people can follow our procedure. So we have a procedure in place for creating estimated values of suspended sediment concentration from a surrogate method. In this case, it's turbidity. So that's an established method that we'll be using. However, turbidity has limitations. The biggest limitation for turbidity, aside from just being overtopped with too much sediment, is changing particle size. So turbidity does very well at looking at fine particles. If you have silts and clays, it does very well. If particle size shifts into the coarser materials like fine sands or medium to coarse sands, the turbidity sensor can't determine whether or not the particle size change happened. And so it could look like there is less sediment, and all that has happened is that the particle size has changed. So one thing that we're doing in this study is we're pairing turbidity and hydroacoustic data together. Hydroacoustic this hydroacoustic sensor is doing a very similar thing that turbidity is doing. It's just sending out a pulse of sound in the 8 megahertz frequency. That sound passes out through particles and gets scattered, and the sensor is listening to that scatter and determines how much of it is being sent back. So it's kind of listening to a response to the sound, and that's happening in the channel, and that refraction of sound is determined to be representative of the amount of something in the water, just like turbidity is, but with light. Hydroacoustic has a similar limitation where it does very well in medium, coarse, and fine sands. It operates very well, but if it shifts into the fine particles, it has a hard time registering those particles accurately. So the goal of this project would be to pair both of those up together and to use the strengths of both instruments to provide a better, more robust record. So this is the project that the product that we're using here. This is manufactured by Sequoia. It's a list ABS. It looks very much like a sonde. Traditional hydroacoustic methods that we use in the survey for velocity mapping or for some other surrogate work are these big giant side lookers. And these are fantastic, but they don't work in very small rivers. They work well in big rivers where you can profile out across with the hydroacoustic instrument. This graph right here is a graph from last month, the same time period as that turbidity graph shown on the previous slide. This is showing the hydroacoustic backscatter from this instrument at the Cedar Hill gauge. Same thing as the turbidity approach. We have a techniques and methods paper supporting this approach to creating estimated values of suspended sediment concentration using a hydroacoustic approach. So this is also a published documented approach. So we have a continuous record of both hydroacoustic data and turbidity data, but we need to regress those data in a statistical regression against some known values. And so we have to go out and periodically collect discrete data. So this is a standard data collection approach. Here we are collecting, this is Keeley-Miltenberger collecting a grab sample. And generally in the USGS, we pride ourselves in cross-sectional data, which represents the entire channel. So we're not biasing what might be passing through the water by just collecting a sample on the edge of the water, but there are definitely times where that is appropriate. And in this case, our instrumentation is mounted right here underneath where Keeley is sampling. So the sampling area of our instrumentation is in this vicinity. And so Keely's collecting a sample that's co-located with our other data. This was done bi-monthly throughout the winter months. And during the snowmelt period, we installed an ISCO automated sampler to collect periodic samples more frequently, because snowmelt period is a very important part of the transport of metals and sediments. So we wanted to make sure we captured that dynamic change more frequently than twice a month. So we have the ISCO sampler that's been collecting a sample every 3 days throughout the snowmelt period. We've done a lot of QA/QC samples too on our procedures and equipment blanks and replicates to make sure that our samples have a minimum level of quality. And this ISCO auto sampler is not refrigerated, and we cannot acidify the samples when they're collected. And so we have done some batch sampling, looking at how much change there is potentially occurring in these samples sitting for a period of a week or two. So that sample is ongoing now. That analysis is ongoing now. This is a batch of samples that were collected. So these are the suspended sediment concentration samples, and then raw and filtered metals samples that have been one set filtered and acidified. The other set is raw and acidified. So we can get at a comparison of the dissolved fraction of the metals transport and the total metals transport. I suppose this probably should have been earlier in the presentation. This is what the site looks like. In this figure, we are looking downstream. Downstream of the Cedar Hill, this is the Cedar Hill gauge here. This is a lot of infrastructure built by our predecessors in the USGS. And a lot of the current nice looking stuff was done by Brian Resin and Fletcher Brinkerhoff out of our office. So here's the pipe, PVC pipe structure. There's 2 of these pipes extending out into the channel. Those have all of our sondes mounted internally. And the cables are running out the top up to a junction box, which is sent up to the data collection platform in the gauge house and transmitted hourly. On this platform here, there's an ISCO automated sampler that's collecting a sample from this same location in the water, so that those samples are co-located with the sonde data. So once we have all of the data for our surrogate analysis, the next component is to build the regression. And I put this here just as a reminder of what regression analysis is. This is the basic simple linear regression. If we were comparing 2 things like the example I gave at the beginning, comparing stage and discharge, that's a simple linear regression. When we start adding more variables, it becomes a multiple linear regression, and we can see which different variables contribute to the correlation. And some of the variables that we have listed here that we are going to be considering include suspended sediment concentration, sediment particle size, and then of course turbidity and acoustic backscatter. Trace metals and metals data such as lead, arsenic, copper. We're also including stream flow as a functionality, seasonality. And then we have the other sonde data that's been operated for a number of years. So we will include pH, specific conductance, temperature. And the last component is a little more tricky, but I think will be an important piece of that. Because up to this point, the regression model will only know that there's sediment or metals present. But if we don't know what the sediment, where the sediments came from, some sediments might look different than others, even though the quantity might look the same. So turbidity and hydroacoustic, they cannot tease out what is a metal and what is not. All it knows is that this is sediment. And although we've seen good regression analysis, just looking at correlation between sediments and things like aluminum, we've seen that a decent correlation in that. I think the model will be improved by adding in a component of the source of the flow. Some areas in the watershed may look very different than others likely do. And so in order to determine the source of flow, We're using a machine learning approach and potentially some simple statistics, but probably more heavy machine learning because we have a rich data set of many years of discharge data that we can tease out at least a coarse source of flow for some of these flow events. This component, we're still in the preliminary phase of, and I'd be happy to talk to anyone afterwards who has some experience with machine learning and source of stream flow. Grady Ball and Justin Nichols are the principals on this, and we're meeting next week to look at some preliminary results of our machine learning. So I should have mentioned this at the beginning as well. We're in year 1 of a 3-year project, and if you were looking for some results like Christina presented, a whole bunch of results. I don't have those. We were still collecting data, but I can tell you that the data are being collected and the sondes are functioning very well. But here are some examples of published results. A couple of years ago, Johanna and I threw together this preliminary graph for a presentation here in this room, where we looked at the regression between sediment concentration and various metals. It's very tiny on my screen. It's aluminum, arsenic, lead, and iron, I believe. But you can see that there's a general linear relationship between sediment and these different metals. Some are better than others. Lead is not really represented well here. But there's other studies that have published results. Allenbach and others published a report in 2017 looking at a comparison of sediment concentrations to turbidity, as well as some other metals that they were interested in their study. And Mast in 2019 published a fantastic SIR about looking at different correlations between metals and various surrogate measurements. So this is an example of what the data would look like that we would end up publishing. This is a real-time gauge. This is a gauge where you could pull up, just like you pull up a stream flow discharge or stream flow graph, you could pull up this site and look at concentrations of suspended sediment or estimated values of suspended sediment. So you could see how much sediment was in the river today, right now. And that has value to water managers. So we, at a minimum, will be producing this, and if there are statistically significant correlation between other metals, we'll publish the same approach to the web for various metals, such as aluminum. Lead probably won't work out. It doesn't look like there's a strong correlation, but the elements that are statistically significant, we can push these to the web in real time, and that's also interesting and important for water managers to understand what's coming down in real time. But the other benefit of this project is historically this is all we knew. These red dots represent physical samples. But we don't understand what happens in between these. And sometimes constituents mirror very well with stream flow, but many of them don't. And suspended sediment concentration is one of those that does not necessarily follow stream flow. So with a temporally rich data set, scientists and river managers can better understand the transport timing and peaks of metals transport out of the Animas River to better understand how these metals are being transported and when. So that is the conclusion of my project. I'll be here all day and we'd be glad to talk with anybody afterwards if you want a deeper discussion than a question, but if anybody has any questions, I'll be happy to take those as well.
They have an non-scientific, just logistical question. That looks like a lot of equipment sitting on the side of the river. How do you protect that?
Oh, That's a great question because we deal with this all the time. We're fortunate to have the Bond family up in that area who it's their private property and it's limited access, and they've always been very gracious to allow us access to our gauge that's there and allow us to put some equipment at the edge of water where we have that equipment mounted. The only traffic through there are rafters, and my experience, rafters are pretty good folks. And so we haven't had anything break or disappear yet. That's a good question. Yeah. Okay, if you have questions, I'll be here.
All right, thank you so much, Jeb. All right, well, we will be shortly here beginning a short break in the mid-morning portion of our program. But I just wanted to make a few announcements here. As a reminder, for those of you who have registered for the field trip tomorrow, that will include presentations and tours of the Navajo agricultural products industry and the NMSU Ag Science Center. Just a reminder, we'll be meeting and start loading onto the buses at 7:45 a.m. in the dirt parking lot that's between Berg Park and the, I think it's Washington Federal Bank. That's right there. So please, please, please make it on time. We'll be departing by 8 so that we can begin the itinerary that we have for that event at the New Mexico Ag Science Center, and then moving on to visiting portions of NAPI. Once again, you have to register for this. We do have a few slots that are a few more slots that have opened up. Some people had to drop out, so if you're interested in that, you can come see me today, or register online as well for one of the few slots that are available. I just also did want to make a note about our afternoon program. It turns out we'll have a kind of a special surprise speaker. Congresswoman Teresa Leger Fernandez will be stopping by this afternoon after an event in the area to give a few remarks to conference attendees. So please stick around for that if you'd like to see some remarks from the Congresswoman. And let me see if I'm missing anything. I don't believe so, but yes, you can all enjoy a short mid-morning break here before we begin with the next portion of our morning presentation, with presentations from Steve Austin and Johanna Blake. Thank you. All right. All right. Well, it's an honor to welcome to the stage our next presenter. Steve Austin has been a senior hydrologist with the Navajo Nation's EPA's Water Quality NPDES program in Shiprock for the past 21 years. In addition to surface water quality monitoring throughout the Navajo Nation, he focuses primarily on addressing impacts from past uranium mining and milling, oil and gas spills, road and pipeline crossings, and illegal dumping of solid waste in waterways. He also headed up the Navajo Nation's monitoring and assessment efforts related to the Gold King mine spill. Steve received a BS in Forestry and Natural Resources Management from Cal Poly San Luis Obispo and an MS in Watershed Science from Colorado State University. Steve, it's an honor to have you here, and welcome to the conference.
All right, thank you. Again, my name's Steve Austin, and I'm actually with the tribe for 24 years now. It's all right. Yeah. What Johanna, Blake, and I will be presenting on today is the study that we're doing with them that's funded under the WIN Act, looking at sources of metals within the San Juan Basin that we're seeing and are monitoring on the San Juan River. And this is a picture of one of our sites located on Gypsum Creek. near Mexican Hat. So just an overview here. Again, there's a familiar outline of the San Juan Basin there on the left. In red, you see the San Juan River cutting through the middle there. The shaded area in yellow is the Navajo Nation. You can see we make up about half of the San Juan River Basin. So we have a big interest in what's going on in the San Juan River. One of the things that I do is collect water quality samples. The purpose of that is to make sure that the waters of the Navajo Nation are being protected for the uses that we put those waters to. For the San Juan River, those protected uses include domestic water supply, fish consumption, primary and secondary human contact, aquatic and wildlife habitat, livestock watering, agricultural water supply, which is basically irrigation. In our monitoring, we've seen periodic high concentrations of metals. And those metals concentrations potentially limit those uses for the San Juan River. So we're interested in trying to figure out where they come from. The main metals of interest are lead, arsenic, aluminum, mercury, and selenium, but it's not limited to those. And we've observed these periodic high concentrations both before, during, and after the Gold King mine spill. So we know that potential sources include, obviously, the hard rock mining, especially the Silverton mining district, which you can see in the upper left there. And there's other mines within the area, abandoned uranium mines and coal mines. On the upper right, we also see that there's illegal dumping that's prevalent both on and off the Navajo Nation. On the lower right, we're looking at the legacy of oil and gas development and production within the basin. This is Flowing Well, which was originally drilled for oil production. It was a dry hole, so they plugged it back to a water-bearing formation and then turned it over to the tribe, either formally or informally. And since it was drilled back in the 20s, the infrastructure's deteriorated and there's flowing now with unrestricted. And we did a study with US EPA back in 2018, looking at about 46 wells in New Mexico and Utah. And we found that a lot of the ones in Utah are actually high in arsenic. So that's another potential source of metals that we're seeing in the San Juan. And then also natural geology. Metals that exist in the rocks and the soil out here. There's not a lot of vegetation, so when it rains, a lot of that sediment ends up in the San Juan River. So we know that our highest concentrations in metals tend to be during the monsoon season when we have that high sediment. So we want to look at the rocks and just the natural geology in the area too as a potential source of those metals. So the objectives of this study are to identify and quantify sources of metals contributing to concentrations measured in the San Juan River. And we're going to go about that by compiling the geochemical information within the basin from published sources, by collecting and analyzing samples from each geologic formation, and some of this work's already being done, collecting and analyzing water, suspended sediment, and discharge from the tributaries, collecting and analyzing water in the San Juan River during the monsoon season. And those two are what the focus of this talk is going to be on. And then this study, again, was funded under the WIN Act, and it's got kicked into high gear this last fiscal year. And we have until the end of September of 2024 to complete it. So the tributary gauge locations that we selected are from just downstream of Navajo Reservoir. Let's see here. So Navajo Reservoir is right up here at Pump Canyon, and worked our way all the way down here to Gypsum Creek, which is located near Mexican Hat, Utah. We have 33 gauge sites. Most of these tributaries are ephemeral. A lot of them, there's no data that we know of. So we have limited data on these, and we're trying to figure out if any of these are a particularly hot spot for introduction of metals into the San Juan. In each of these sites, we installed this SEDChem gauge, which was developed by EGS, basically by Jeb. And what we're trying to collect at each of these tributary sites is discharge, water quality, and sediment. And these gauges are designed to do that. So getting at the discharge part, like Jeb had talked about, we have this PVC pipe here. Inside of that is a pressure transducer, which measures the depth of the water. within these channels. And then with the work that Jeb's going to be talking about in the next presentation, the mapping and modeling will give us a discharge, how much water is flowing out of these tributaries and into the San Juan River. We're also looking at water quality, and that's in this larger PVC pipe, which is opened up right here on the upper left, upper right. Inside of there are 2 1-liter Nalgene bottles. They have a tubing coming out here. There's ports at 2 different levels, so we can collect water at 2 different stages during a flow event if it gets that high. And then we have tubing coming out the top, which allows for the venting of air as the water is coming in, so that there's uniform flow of water into these bottles. And then the last thing we have is the sediment trap right here. And then this is just one located in, I think it's Comb Wash out near Bluff. So how did they do this summer? We had a really productive, let me switch this back over. There we go. We had a really productive monsoon season, which was really good for us. This is Red Wash, located just west of Shiprock, near the Four Corners area. The gauge that we had installed there is located right about here. And these 3 pictures are what it looked like about a week and a half later when it dried out. Jeb and I went out there and it was completely inundated. It actually held up pretty well. You can see a lot of debris on it, got knocked around a little bit. This is a pressure transducer, but it really held up well. And when we opened it up, we ended up getting more sediment than water in our water sampler. But again, that's good information that we need. Some of the other gauges, you can see these 3 right here did really well under high water flow conditions. Excuse me. This one's in Coots Canyon, and yes, that is a boat. We're not sure why it's in the middle of that ephemeral or that wash, but it did end up washing away this summer. This is in Salt Creek Wash near Shiprock. This is Mancos River down near the mouth. Those all held up pretty well. Being inundated, that Mancos one was 8 to 10 feet underwater at one point. So we had some big flows in these washes we learned this year. And then this is in Largo Canyon. It got washed downstream. This is gypsum. It got washed downstream a couple times. And this is Many Devils Wash near Shiprock. So some of them got washed away and we were able to recover. And there's a few that are either in Lake Powell or somewhere buried in the San Juan right now. But we learned a lot this summer. A lot of these we found better locations for, and we're still trying to figure out good locations on other sites. But these were very useful. In addition to those SEDChem gauges, I went out with my coworker Fred Johnson, and we went out and grabbed samples during these storm events. So we want to actually capture the flow in real time as well as during having these passive samplers out there. One of the advantages of going out there and grabbing it is we know what's going on at a specific time, and we can document some of the conditions too. Those SEDChem gauges are passive. We don't know exactly when they grab samples, and there could be a compilation of storms in those. So this, we went out and grabbed samples on the San Juan because we want to see various parts of the hydrograph. When a storm comes through, we want to, if possible, track these storms downriver. So we had 13 locations on the San Juan. We go out and just do a grab sample with a 1 liter bottle. I was able to grab 120 samples roughly over 16 different sample events. So typically grabbing between 7 and 9 samples on the San Juan. From top to bottom, we're looking at just upstream of Largo Canyon down to Mexican Hat, and it's roughly about 160 miles of territory. So we weren't able to do the whole stretch every time, but we were able to get good sections of the San Juan when we did do it. In addition to that, we're also grabbing from those tributaries at the same time. So again, so we could see what's going on in the San Juan and in some of those tributaries. We also want to try and get upstream and downstream of some of these major tributaries on the San Juan. We ended up having about 34 sample sites on the tributaries. In some cases, on Chinle and on Chaco, we also did some sampling further up in the watershed. Most of them were down near the mouth though. And we ended up grabbing 100 samples in those tributary sites. After the season was over, we went back to try to figure out what was going on when we grabbed these samples. So on the top, you see there's daily precipitation totals. It's kind of hard to see the outline of the San Juan Basin here on these other maps, but we'd go back and see what was going on storm-wise a couple days before we grabbed our samples. Just give us a general idea of where in the basin the storms were occurring, what intensities were probably going on, and then give us an idea of why some of these tributaries were flowing and what we were grabbing. In addition to that, we'll go back and look at the hydrographs. So there's 7 or 8 stream gauges on the San Juan River. Plus we had the Animas and the La Plata have gauges that have been in existence for a long time. And this summer we added 4 gauges, again, using Wind Act funding at the mouth of the Mancos River, the mouth of the Chaco River, mouth of Chinle, and mouth of McElmo Creek. And so all that information we were able to use to try and figure out what was contributing to the flow that we sampled when we sampled that. So for real time, we relate our sample location to the nearest gauge, and that could just tell us a little bit about what part of the hydrograph we were sampling. What I ended up also doing was taking into account travel time between gauges and lined up all the hydrographs to see maybe what tributaries were flowing, what was going on in the upper San Juan at the same time, and see what was contributing to the flow at that specific site. And just to kind of run through that real quickly with a fairly simple one, was this event on, I think it was August 19th. It's covered up on August 17th. So sample site at Aneth, which is just downstream from the Four Corners in Utah. This gauge site right here is Bolac Ranch. So this is the upper, basically covering the upper San Juan. We could see it was pretty flat during the storm event. So it was base flow coming in from the San Juan River. Then we go downstream a little bit to the Farmington gauge, which is this yellow one, and we could see some event came in. And if you drop down here, all the solid lines are San Juan River gauges, all the dashed lines are tributary gauges. You drop down here and you see that this is the Animas River, which comes in just upstream in that Farmington gauge. So we know that this is a combination of base flow from the San Juan combined with Animas River flow. Down here at Fruitland, you see that we're picking up the La Plata, which comes in just downstream from that Farmington gauge. And then this Four Corners site looks like it's a good combination of those three, the upper San Juan base flow plus La Plata and Animas River storm flow. And then just another example would be this Four Corners site with these gauges all lined up. We see that we're losing the La Plata, but we're picking up the Chaco River. Sorry, I didn't have my laser pointer. So yeah, so this is the La Plata right here. This is the Animas. This was the upper San Juan. This is the Farmington site. And this is Four Corners at Aneth and the San Juan River at Four Corners. So we're picking up the Chaco on this last site right here. And then one last slide real quickly. Another thing we looked at was every time I would grab a sample, I grabbed a small 40 milliliter vial just as a reference. I started doing that after Gold King to kind of show that other events cause changes in color in the river. And this actually provides a good qualitative analysis of what was going on. When you take pictures of a site, different lighting causes differences in color. So it's really hard to compare what was going on at one site versus another site just by looking at field photos. This allowed me to look at colors and color variations under the same conditions by just putting all these together and taking a picture of it. So on this one, we're going downstream from the Hogback to Mexican Hat, and you can see the variations in colors on the San Juan. And then these are all the tributaries I was able to sample on that same day. And you can just kind of see, it gives you an idea, there's a lot of stuff going on. The colors can kind of tell you which ones are contributing at what time. And this gives you also an idea when you settle it out about relatively how much sediment you're seeing at the different sites and the different tributaries. And when this one, I allowed it to settle 4 days before I took this photo. So you could also kind of get a feel for there's more finds, for example, in the Chinle site here versus McElmo. So there's a lot of interesting information we can grab qualitatively just by looking at the sediment in these vials. And this photo's added here just to kind of show you that, not surprisingly, these tributary colors look a lot like the geology as you go from upstream to downstream on the San Juan. Now I'll turn it over to Johanna. Also, we have a couple of fact sheets, not a lot, but I have them if you're interested in the back.
Okay, thank you, Steve. And will you and Johanna both be taking questions at the end? Okay, you can just come up here, and you can both come up here and you could take one of the mics at the end for the Q&A if you'd like. All right, so let's move on to Dr. Johanna Blake. She's a research hydrologist with geochemical expertise at the New Mexico Water Science Center for the U.S. Geological Survey. She's devoted her career to understanding geochemical processes that may affect surface water and groundwater, especially related to rock water, sediment water, and ash water interactions. She's been the lead scientist in New Mexico working on post-Gold King mine spill research in the Animas and San Juan rivers, and has worked on understanding potential effects of mining on 2 drinking water reservoirs along the Animas River. Dr. Johanna Blake, thank you so much for presenting today.
Thanks, Mark. Oh, boy. I feel like it's gonna fall over on me. I'm too short. Hold on. Okay, there we go. Okay, thanks, Mark. And thanks to my co-presenter, Steve, and the Navajo Nation Environmental Protection Agency, and especially Steve Austin and Fred Johnson, who are our partners in crime in this project. It's very much a collaboration, as Steve has shown, and the USGS team is just, we're just so thrilled and proud to be able to be a part of this. So I'm going to go as quickly as I can because Jeb accuses me of taking up his time because I talk too much. So basically what I'm going to do is show you some of the chemistry data, okay? And so Steve did a great job of providing kind of the intro of what it is we're doing and why. I've put the objectives and the approach back up on the screen just to remind everybody. The image on the right here shows a conceptual model of the ideas here of what inputs are going into the San Juan River and where are they coming from. And so this image on the right is also part of this fact sheet that Steve mentioned. So we had, as Steve showed, a very busy fiscal year 21 monsoon season. It got to the point where it was like, oh my gosh, would it stop raining? And you don't want to say that in these regions, but it really, the Four Corners region really got quite a bit of monsoonal moisture last summer. And so these are some numbers that I had put together. 70 sites sampled, including the San Juan River and tributaries overall. And of course, you see the size of this watershed, it's quite large. We did a synoptic sampling event last February. And what a synoptic is, if you're not familiar, is essentially you're trying to measure the water as close to the same time period as possible. And so what we did is we went in the San Juan River and collected water chemistry samples in February throughout, a matter of a couple of days. And that information was providing kind of a base flow understanding of what the chemistry is in the river when there isn't moisture. So, wasn't snowing, wasn't raining. It's that lower level of water, and kind of gives you a background of what the chemistry is. And I'll show some of those results. We had SEDChem gauges in that bottom bottle that Steve showed. We had 81 of those, 60 in the top, and then 244 grab samples, which most of those came from Steve and Fred. And so from last year, we had a total of 404 samples, which is quite a bit, considering that when we were budgeting this, we weren't even close to having that many that we were thought of. So it's wonderful, it's wonderful to have all of this data. And you can see, again, the outline of the San Juan watershed here, and shows the number of samples. I imagine it's kind of hard to see, but we do have calculations of and notes of how many samples at each site. Is it a grab sample? Is it a bottom sample? Because we want to compare and see what sort of information we're finding out depending on how the sample was collected as well. Real quick, and I know you're not going to be able to read this, but it's just for an example. We have the geology from each watershed. So we're going to go through and parse out every single watershed, see what the geology is there, see what the chemistry is in the geology, and then see how that equates to what we're seeing in the outlets of each one of these tributaries.
wanted to just show a couple quick bits of information from some of the published data that we've been working with. And so these are published sediment chemistry results from a data collection campaign that happened in the late 70s, early 80s, which I realize is a while ago, but sediment doesn't generally change that dramatically. So this is part of what's called the National Uranium Resource Evaluation Program. If you want to look that up, it has data from across the country from sediment and water. And the spatial extent is really quite good. This was a time when ultimately the goal was to look and see where there might be uranium, but what it has in favor for us is that there's a lot of other elements that are provided in this data set. And so you can use these data to see what's happening in a broader watershed. And so that's what we're looking at here. And this extent shows the concentrations of aluminum in weight percent. So aluminum is a pretty major element in certain geologic units. And so you see those concentrations overall as a higher concentration than you might something like arsenic. And so in this particular figure, I'm showing the lowest bin of these different colors on the map there is half the crustal average. So that's the average concentration in the Earth's crust of that particular element. And that can be useful for comparison. So you kind of get an idea of, okay, is this kind of roughly, you know, a general concentration, or are we seeing anomalies that are higher than that? So the way I have this plotted is the lowest is, you know, the lowest values to half that crustal average, then half to the crustal average, and then two bins above that. So essentially, when you're looking at this, the more red, the higher the concentrations. And the takeaway here is that at least for aluminum, you're seeing higher concentrations towards the headwaters and middle section of the reservoir, or excuse me, of the watershed. Too many different terms in my head here. Showing the same thing here for lead and uranium. Didn't have arsenic data in the data set, so I need to look into that a little bit more. And so, you know, same idea here where you're seeing higher concentrations of lead further upstream. However, you can get, you know, small locations where you might have a high concentration of lead that then you could see in the water or the sediment. And so, you know, on this scale, it's kind of hard to see, right? But this is just an example of where we're going with this. And then the one on the right, you can see for uranium, I mean, there's a lot of uranium in this region. And so, and we're seeing that in a fair bit of the water as well. Okay, moving along. So here's some preliminary results. And the next few slides I'm going to show you are preliminary results from the samples that we've gotten back from last year. We don't have all of the 400 samples back yet. COVID caused a lot of backlog in a lot of laboratories, and so we should be getting those data back very soon, but we do have enough to show kind of where we're headed with things. And so this slide shows the synoptic sampling from February 2021. So again, that was where we went and sampled along just the San Juan River over a period of a few days. And the left y-axis shows the concentrations of arsenic, lead, and uranium in micrograms per liter. Okay, so that's parts per billion. And aluminum also in micrograms per liter on this side, but it's on the right-hand side because the scale of it is so much higher. Excuse me. And the flow direction, because of the way the watershed is, that the way my brain is sort of working is, okay, well, to the right of the screen is upstream and to the left is downstream. And so the very first site here is San Juan River near Archuleta. The majority of these locations are co-located with one of our stream gauging stations. And so that way we know what the stream flow is as well as what the chemistry is. And that's going to be important in the long run, because if you have a concentration, let's say, you know, a high concentration of arsenic, but a very low quantity of water, the input ultimately is not going to be as high. Okay, so we call that loading. And I think Jeb will probably talk a little bit more about that in his next talk. And so really the takeaway here is that the values are pretty low in general. And it is interesting here to point out that lead and aluminum especially take kind of a reasonable rise as you move downstream, which is pretty interesting. But again, remember, this is at base flow. There's no rain coming in. There's, no snow melt at that point. Okay, so keeping that in mind, the next slides I have are data from the monsoons, and I have on each slide, and I'll go to it now, a blue line that sort of shows the range of the base flow data from the previous slide. Okay, so oops. Sorry about that. And again, same thing where the river flow direction is going from the right side of the page to the left. I put just a couple notes here so you can orient yourself. So Archuleta is the first value. Four Corners is kind of, midway towards the left, and then Mexican Hat is at the end. The blue squares are the San Juan River samples, and then the orange circles are all tributaries. I did not separate out the tributary data from grab samples from the SEDCHEM gauges, just because of time, right? If I had several hours to go through this with you guys, we could do that. And we will ultimately, there's going to be a huge suite of papers that come out about this. Okay, I have a few minutes. I don't want to run over Jeb's time. And so, yeah, in addition to the base flow range I have here, I also have whatever the drinking water standard is. And so in this case, the arsenic concentration is 10 micrograms per liter. So you can see that as a comparison. And you can see here that overall, the concentrations of arsenic are above what that base flow was. And you can start to see where maybe there might be some inputs coming in, especially as you move downstream. And you have quite a bit of a spike there. Going on to lead, set up exactly the same way. You can see here that a lot of the samples are above the 15 microgram per liter lead goal. And you can see how there's kind of some variations in the San Juan River samples as it goes up and down. And then you also have some spots where there's quite high inputs. So, we don't have big conclusions yet, but I think this is just sort of a little bit of eye candy as far as, hey, look, what Steve and Fred have been seeing is legit. And not that I didn't think it would be, but, we're starting to really focus in on what it is that that is contributing to these particular elements in the San Juan River and where. And of course, we want to go even further and try to figure out, what potentially is the source. Here's uranium. Just sit on that for a minute. Same thing, seeing some variation and some spikes from certain tributaries. And then the last one here is aluminum. And again, same thing. There isn't a drinking water standard. Oh yeah, there is. Sorry, it's all the way down at the bottom. Secondary MCL for aluminum. And so, we are seeing these variations. We're certainly seeing these concentrations above what we saw in that base flow sample. And so, as we continue on, we're about to start the monsoons for this year. Hopefully there's rain throughout the whole state, but certainly in this area for this project. And just continuing to put all this information together. I'm happy to talk more about some of the other things we're doing with geology. We did scanning electron microscopy that if anybody saw Rachel's poster yesterday, where we're looking at the mineralogy of each different watershed. So lots of other parts to this. So continued plans, I think I already touched on a few of these. Sampling for monsoons, we're looking at the geology, chemistry, and then of course calculating the stream flow and the tributaries, which Jeb will talk about next. And with that, I will say thank you, and hopefully we have a few minutes for questions, but I know I'll at least be around the rest of the day if people want to talk specifics. So thanks. And only 1 minute into Jeb's time, so it's good. Any questions? Okay. Well, like I said, we'll be around. We do have a handful of these fact sheets if anybody would like a hard copy. If not, they're online as well. If you search for, I think it's tracking the source of metals to the San Juan. Yeah, thank you.
Okay, thank you, John and Steve. All right, and our last morning presentation here before lunch, a man who needs no introduction because he already had one this morning, Jeb Brown.
Thanks, Mark. I think those biographies are often pretentious anyway, so let's dispense with that. There are two kinds of people. One is the quick presenter, and then the other was the professor presenter that can't present under 40 minutes. And so, Johanna, you're fantastic. It's also not fair to shoehorn her into 15 minutes because she knows a lot. So I'm going to go quickly through this so we can get out on lunch on time. Also, a lot of this is covered in some of the other presentations because this is a component of the large San Juan source tracking project that Steve and Johanna just covered. Let's see. I need to acknowledge the great folks I'm working with. Johanna, of course, Grady Ball and Keely Miltonberger, who are not here. Zach's here, of course. And as well as some other folks who aren't added as co-authors, and that would be Steve Austin and Fred Johnson with Navajo EPA, and a new crew inducted this week, Caleb Van Zanny and Rachel Mixon, who when you trudge through a mucky channel and vegetation and waders in 100-degree weather, you gotta get some kind of credit. So I appreciate you guys' hard work. Here's a photo on the left of Many Devils Wash and some of the uranium issues in that area. And then on the right, I just wanted to list, give you a visual cue of some of the important work that we're doing in trying to identify sources of metals that are making their way into the San Juan River. And then on the right is an image of Fred Johnson and I flying at Salt Creek, I believe. So the goal of this component of the project that I'm in charge of is to help quantify the metal loads to the San Juan River from these various tributaries. Like Johanna mentioned, it's important to understand how much of these materials are coming into the San Juan River to understand the context for what those values mean. And as you can see from the spatial extent of our project here, the yellow pins are the different ungauged ephemeral arroyos. Actually, I think a handful of these actually have gauges on them, so that's not exactly true, but there's something like 35 gauges, 35 of our locations that do not have USGS stream gauges. But we still need to know the stream flow from those ephemeral channels. So quick overview on concentration versus load. Johanna covered this nicely, but if you think of a tablespoon of salt and you dump that into a glass of water and take a sip, it's going to taste pretty salty. If you threw that same spoonful of salt into the pool and dove in, you wouldn't even know that it was there. And so the quantity of the mass of a constituent per volume is concentration, but the load is that amount over time. And so if we take a sample at one point in time, we don't understand how long that persisted. We don't understand the load. So one thing that we're missing is if we collect a sample, we have the concentration, but in order to calculate load, we need to know the stream flow, and that's the volume of water per time. You're probably familiar with something like this you've seen out on the landscape. This is one of our standard USGS stream gauges. I believe this one is at Mineral Creek up near Silverton. This is kind of a standard looking USGS gauge, a lot of infrastructure. Get my laser pointer up here. There can be quite a bit of infrastructure depending on the site. Often we need something to measure at high flow where we're not going to get in trouble of being drowned or hurt. So that's often at a bridge or a cableway. The cableway can be very expensive to install and maintain. So here's an example of some infrastructure that's been put in place. A gauge house inside here is a data collection platform, solar panel to charge the system, and then this antenna here to transmit data every hour. This is the infrastructure that goes into a USGS stream gauge. And this is the anatomy of what one of those gauges would look like. This figure was in my previous presentation here, but a little bit more information about that gauge is this is a stilling well that's connected to the river, which allows water to flow in and out. And as the river rises, the float inside the stilling well rises. And that change is detected at the top here with a spindle that turns. And those data are being recorded and transmitted hourly. We have some other methods for measuring stage now as well. We use differential pressure, or I'm sorry, not differential pressure. We use a pressure sensor to determine the amount of water above the sensor, or in this case, the bubbler end of the line. We also use radar to determine the height of water as well. So this is the value of stage that's being collected, which can be costly to install and operate. And then I reviewed this previously about how we create a stage discharge rating curve. If you picture what that would take, monthly visit for a few years worth of stage discharge paired data, somebody to measure the geometry and velocity of the channel on a site visit, and then to do that over the range of flow from low to high every year and develop a reliable rating curve that takes time and a lot of money. And this is why USGS stream gauges can be costly to operate. It takes quite a bit of infrastructure and salary to get to this point here. And if you recall, I'm going to make everybody sick by flipping up here. If you recall, the number of gauges that we're looking at here and that we need stream flow at, it's not practical in the scope of the budget in this project to operate 30 plus gauges for a number of years. In addition to that, in order to measure stream flow, there needs to be stream flow. And these gauges are all ephemeral and rarely have flow, and the odds of you being there to measure that stream flow is very, very small. So because of these reasons, we're tasked with the job of creating something and finding a different approach to quantifying stream flow. And that's the goal of this project, is to provide some ballpark number of stream flow. So the first thing we need to do is collect stage data, and that is being done with this rugged troll stage recorder. These are fairly cheap. They're $500, $300 to $500. And they're installed, like Fred or Steve had mentioned, in that pressure transducer pipe mounted on the SEDChem gauge. And I've included here, this is the wrong figure, but I will tell you what the axes say. I didn't label this, I apologize. On this y-axis is stage in feet, and on the x-axis is time. I think it was over the course of a few days last summer. This is marble wash. So you can see here the trace of the height of water in a channel over time. So with these fairly affordable stage recorders, we can collect stage data, but we still need the channel geometry. We know how high the water is. We don't know the channel geometry, and we also don't know how fast the water will flow down that channel at any given height. So the first step of that is to get the channel geometry. And to do that, we're using fairly cheap and accessible drones. The drones that we're using are the 3DR Solo. It's about yay big, size of a backpack. And off the market, when they were on the market, they were about $500, so fairly cheap. And we also used a digital point and shoot camera. This one's made by Ricoh. It's actually the GR2. So that camera is mounted underneath the drone and flown above the area of interest, above the channel that we want to model. And we collect aerial images that are used to model that geometry. And I'll go over more of that process in just a sec. One of the pieces of data that we need in our aerial imagery is a way to rectify the model so that it's true to each other. All these different images are related to each other and are able to be laid over the surface of the earth. So when we do our process at the end, the model can be twisted or contorted. And so we need to give the model some positional data to rectify that. And these are called ground control points. And on the right is an example of the historic way we've gone about this, which is a 2x4 thin panel of MDF that's spray painted with a grid pattern so you can see it from the air. We'd lay those out, usually 5 to 10 of those over the landscape, and then walk around with a RTK GPS rover and shoot in all of those points. That could be very time consuming, adding many hours to the process. And so we have available to us these arrow points, which are made by a company called Propeller, and they have an internal GPS that's powered by a solar panel. And 10 of these are laid out on the landscape and collect data during the flight. And then we can take that ground control point and correct the imagery. Here's an example of what that would look like. On the left-hand side, the bigger image is showing an aerial camera from the Many Devils Wash. And if we zoom in on this inset zoom box here, you can see the traditional gridded 2x4 rectangle next to the propeller device. So when we're doing post-processing, we'd go through the image and look for these positions and pin them with specific coordinates. If you look real close right here, there's a little white dot that I'm covering with the laser pointer. That's where the said chem gauge is located at Many Devils. Before anybody gets really excited and wants to change their career or go back to school to fly drones for science, I want to discourage you that it's not that exciting. After launch and takeoff and planning for days, doing all the paperwork that we need just to get in the air, and not thinking about the hours post-processing, the fun part is getting this drone up in the air. And once you do, you hit autonomous flight, and it flies a gridded pattern. Which is really cool from a science perspective to see that you're sending this little robot on its way. But it's also important from a quality of data collection. This camera is operating here. There's that GR2 Rico digital camera. It's collecting a picture every 2 seconds. And it knows, based on the camera settings and at what height we're flying, it knows what overlap and side lap it needs to build a good model. And so it's very important that we fly exactly along these gridded patterns or as close to them as possible. So we get a really good data set, and the autonomous flight does that very well. So unless something goes wrong, it's a pretty boring flight. Once it runs its gridded pattern, then it's done, and we bring it back and land. One of the limitations of this approach is that photogrammetry, which is the process I'll talk about on the next slide, it requires that you're able to see whatever you're interested in modeling. And for our application on this project, we want to see the channel geometry. Well, if there's a bunch of cottonwoods and willows, we would see the tree geometry and not what the channel looks like. Fortunately, or unfortunately, as the case may be, we live in a very arid climate and there isn't a lot of vegetation. So for the processes here, we can see bare earth at least well enough to build a good model. And so I'm showing a couple examples here. On the left, this is the farthest site downstream, Steve. It's that site, gypsum. Farthest site downstream, where it's a beautiful bare rock environment. You can see geology all over and not a lot of vegetation down by Mexican Hat. It's fantastic. It's also a great candidate for taking aerial images and building a model. The right-hand side is Red Wash. We're out flying that site and also just showing the bare landscape that lends itself well to modeling. So when we get back with the images and our data, our ground control points and our digital pictures, we take those pictures and import them into Metashape. And Metashape takes these. I did not tell it where any of these cameras were. The cameras are not tagged with GPS data. The software looks at the images and compares them with each other and lines them up exactly where they would be. So the powerful software then through some data control and quality, we eliminate some of the cameras. For example, where we have turns where the image might be at an angle because the aircraft was turning. Or also our launching and landing areas behind this area. We'll be eliminating those and then making some decisions that we want to apply to our data to make the best model that we can. So we do that over a number of processes. And Metashape takes those decisions, and then each digital image looks for comparable positions in other images, and then does the math to figure out where those positions are in relationship to each other. This is why it's important to have side lap and overlap that's sufficient to build the model. After doing calculations for a number of hours, depending on your video processing power, and some old machines, this can take up to 12 hours at each step to process. It's a lot of computation going on in the background. Then you end up with, underneath here, you can see the outline of what looks like a three-dimensional picture of a river channel. If you were to zoom in on this, you would see millions of individual dots, and all of those dots are an XYZ coordinate that build out the digital model. So with that process, we can make an orthomosaic that's a very high resolution detailed picture of the land surface at the time we took the images. But we're interested in a digital surface model. We want to know, what does the geometry of that channel look like? And so here's a picture of a DSM that shows in warmer colors the higher elevation and cooler colors the lower elevation. So that gives us the channel geometry we need in order to model stream flow. So the next step is to model the stream flow. This is using the slope area computation tool in IRIC. And it basically pulls out different cross sections across the stream profile and shows the geometry. And then we route flow through that at different heights. And if we know the flow at different heights, that lets us build a stage discharge rating. So the challenges and limitations are, well, why wouldn't you just do this everywhere instead of paying USGS thousands of dollars to run a traditional stream gauge? And like many things, challenging questions requiring challenging approaches also have their limitations. And so one of the limitations is, as Steve showed, these gauges get moved around. I showed you the traditional stream gauge is a very well-installed piece of equipment that is maintained frequently, and we shoot levels to that every period of time, and I'm not remembering when, it's a year or two, but frequently to make sure that the reference points are not moving. Because if your reference points or your sensor is moving, it may look like there's more or less water than there actually is. So that's one of the challenges here. We're operating with non-optimal positioning. We could have our stage data off by, in the positive or negative value. Steve's not a challenge or a limitation, but post-flow event, this equipment being buried by bed material is. So you can see here, Steve, this comes up to his kneecaps here. He's a tall guy, but this is about 4.5 feet of T-post sticking above the channel. So after this flood event, there was on the order of feet of bed material deposited in the channel, and that affects the channel geometry. So when we're calculating stream flow and giving estimated values of stream flow, that's assuming that that channel geometry stays consistent over time, which it probably is not. Another challenge and limitations here is things being moved out of the channel. So if you get a lot of vegetation being removed, that affects the roughness coefficient of velocity moving down a channel. And I included this this boat again because It was so bizarre to see a half-buried boat in the middle of a river channel. But here it was on this site visit on the right, and our gauge is somewhere over here, just off screen. And a few weeks later, after a really big flow through the channel, our gauge is here. And this is where the boat was, and it's gone. So, you know, this is just an example of some of the channel changes that can take place. So in conclusion, we have a lot of limitations with this data, but sometimes, you know, with a good model, all models are wrong, but some are useful. That's the approach that we're looking at here is we don't know exactly what the flow is, but we want to get a ballpark estimation to put the load in context. The contribution of different metals from different ephemeral channels in context. So I think that's all I have. I'd be happy to talk afterwards if anybody wants to dive into any of the details or pursue a career in UAS, US for science. So with that, I'll take any questions. Oh, there you are. Hi.
So this is really interesting with the camera. Do you think that LiDAR will ever catch them to shoot LiDAR?
Oh, yeah, I should have mentioned that. So what we end up with in this data set is a DSM with comparable resolution to LiDAR. We can get sub 2 centimeter accuracy on the vertical. But it has its limitations. Like I mentioned, we have to see the Earth's surface. We only can fly a very small area, but it's cheap. LiDAR is very expensive, but you can cover a much greater spatial extent. And you can see through vegetation and tear out the vegetation. You can get first return, you can get bare Earth. So there's definitely limitations. But that being said, there are some small payloads that won't work on this aircraft that we have, but there are people in the USGS who are using small LiDAR on unmanned aircraft. But again, they're expensive. So it's a balance between the kind of data we can generate versus the cost. But yeah, it's definitely technologically available.
That's an question. So you have some action plan, is that part of your department to stay?
Well, it's a nice position to be in the USGS. We don't get the chance to make any policy changes, but we offer the data to other people who do. So the other folks in the room who have policy and management oversight would take these data and say, well, as an example, it looks like this watershed is one of the major contributors. Let's try to do something about that, of whatever it is, lead or uranium, whatever that is. Or, you know, conversely, it looks like a lot of this material is coming from the natural geology of the Manco Shale. Is there anything we can do about it? We're offering some of the science solutions for people to think about what to do with policy and management. All right, thanks.
All right. Thank you, everyone. Thank you to all of our morning presenters. Okay. So we've wrapped up just a few minutes early, so I believe they're just about to set out the lunch food for our buffet today. So while they're doing that, I'll just take another moment to remind people about our afternoon program and let everyone know that at around 2:15 this afternoon, we'll be hearing remarks from Congresswoman Teresa Leger Fernandez. So be sure, if you'd like to stick around for that, to join us this afternoon, as well as for more of our wonderful afternoon presentations. I figure this would be a good time as well to give a few shout outs to the people who have helped on the technical, the organizational side of the conference. So I just wanted to say a big thank you to the New Mexico Water Resources Research Institute staff who've been really key in helping out today and before the conference, after the conference as well. So we have in here, we have Anik Alvi. We also have running around, taking photographs, Kaustav Nopone. We have Mary Beth Ewing and Jeanette Torres that are out there at the check-in registration area. And Marcus Gay as well, who's been helping out with numerous things throughout the conference. And a big thank you as well to San Juan College for once again hosting this year's conference as the venue, or I mean, being the conference venue for this year's conference, especially to the staff, Chris Rosen, Robert and Josh, who've been a big help in making this hybrid conference possible. This is a big first step for us as an institute to do both a in-person and virtual conference together at the same time. So big thank you to them as well. As we near the end of the conference, I'll have many more thanks and some closing remarks to give. But while we had a few moments here, I just wanted to say thanks to those people as well. Nope.
July 13th.
Oh, would you want to come up to the microphone and just tell everyone about the event that you were?
Sure.
Okay, thank you.
I just heard on the radio this morning. This is for 10 minutes. There's going to be on July 13th, an economic development conference right here at South College. More information to come, but it's on the level. A lot of interest. I just heard that. So, all this stuff. All that stuff.
Okay, thank you so much for the information on that. Like I said, yes, this afternoon we'll be hearing presentations from Dave Dubois, Susan Beharry, Shelley Lemon, once again, along with a co-presenter, Lucy Parham, and closing out the conference presentations today at 3 p.m. Maggie Hart-Stebbins from the New Mexico Office of the Natural Resources Trustee. And let me see, are we ready for lunch now? A few more minutes? Okay. Well, I'll leave the podium here, and in a few minutes we can all start making our way over to the luncheon buffet. But thank you all, everyone, for attending so far this morning, and we'll look forward to seeing you back here at 1:15 when we begin our afternoon program. Thank you so much. Okay, everyone, if we could all start making our way back to our seats, we can get started here with the afternoon portion of day 2 of the conference. Okay, and starting out this final afternoon, we'll be hearing a presentation from Dave Dubois on the climate outlook of the San Juan Basin. I'll just start off here with a little introduction of Dave. Dr. Dave Dubois is the New Mexico State climatologist and an associate college professor at New Mexico State University. Dave focuses on climate literacy by providing climate information and education to the public. He is also the New Mexico Community Collaborative Rain, Hail, and Snow State Coordinator and chairs the New Mexico Drought Monitoring Working Group for the Governor's Drought Task Force. As the state's climatologist, Dave directs the New Mexico Climate Center and oversees a network of automated surface weather stations throughout the state. Dave is a native of New Mexico and grew up on a farm in southern New Jersey, excuse me. Dave has physics degrees from Rutgers University and NMSU and a doctorate from the University of Nevada, Reno. Dave, thank you so much for being able to present at our conference. Let me pull up your slide presentation here. All right, the floor is yours.
Looks like you got the right conference. It's always good to be in the right place. So thanks for that introduction. We'll talk about where we stand in our seasonal climate weather patterns, and we'll touch a little bit on kind of the future. You know, as climatologists, people think we have these crystal balls that we kind of consult, and you know, we burn incense or something like that, and nothing like that. It's not as interesting as that. We rely on computer models and try to figure out, just like you all, you know, what the weather is going to be. But you know, it's a matter of what kind of tools we have. So I want to talk not just about the New Mexico side, but the most parts of the Four Corners. So on both sides of the, there's really no borders when you're talking about climate, really. So let me figure out where the buttons are. Good. Okay. Well, I just wanted to kind of go over you. I'm sure you've seen these kind of graphs before. If you haven't, this one is a graph of the snow water equivalent. This one is over the San Juan Basin. So it's a combination of looking at a bunch of the snow telemetry weather stations out in the higher elevations, 9 to 11,000 feet, looking at how much liquid amount of precipitation is in the snowpack over the whole water year. Remember, a water year starts in October, goes from October to the end of September to next year. So this is the snow water equivalent over the San Juan Basin from October 2021 to the present, pretty much. That's the black line. All the different pretty colors in there are the different percentiles. And so there's a really faint green line, which is sort of pretty close to the black line. So if you were to look at kind of the comparison to normal, we call that's a 30-year average. It wasn't too bad, actually. We've had some stretches where there was not very many storms at the flat area right around in November, December, but then we started to pick up snowpack, got above the average. Right around January, we saw some nice January storms, and then it flattened out again. And then we got a little uptick in storms, kind of late season, but then it melted out about somewhere around 30 days in some places before the average. So if we look at the totals for the snowpack, it wasn't look too bad. Actually, if you were to ask me that question back in March, we were pretty close to the median. You know, it's like, yeah, it's pretty good. But we're in this phase of that is called the El Nino Southern Oscillation. And so we're in the dry phase of that called the La Nina. And the strength of the La Nina really depends on the amount of moisture it can pull in, the storm tracks that come over us, how much of the storm tracks will bring moisture from the Pacific to us. During La Nina periods, we tend to get less snow, less precipitation, and as such, we get a little warmer average temperatures. And so it's been during a La Nina. I usually tell folks, if you see that in the news, expect drier and warmer winters. And so that's pretty much the case for La Ninas. We've got two, and I'll talk about the next one. If there's another one coming, we'll see. But that's kind of a story we're seeing a lot of parts of along the Colorado, as well as in southern the San Juan, even the Rio Grande Basin. Very similar type of graph that I've been showing, and we look at these as climatologists. I do a weather briefing myself every day of the year, and just kind of looking to see where the snow is. Is there snow coming, and where is it? And so we've been looking at these, and we're really hoping to get more snow, but we weren't expecting. We always have hopes, but the expectation is we know it's not going to it's going to be another dry one. And so how did it pan out in terms of temperatures? So this is a graph that has a lot of different colors on it, but if all the warm colors show that it's above average. We tend to put things in terms of percentiles. So from 0 to 100, if it's toward the high end, that means it's on the warmer end. If it's on the 50th percentile, that's like the median. It's sort of, that's sort of like average. And then if it's below average, so you would color them green or blue. As you can see, there's not a lot of blue or green on this map. It's mainly either white or yellow or even red or orange. So that tells me this is the water year total average temperature. How does it sit in terms of ranking compared to all other years going all the way back to 1979? So if you look at that October to May, and then compare it to every October to May all the way back to 1979, how does that rank? So you can see pick your area, your favorite area, and you can translate the color and see like if you look over Farmington, it's sort of in that light orange to yellow. That's sort of in that 70 to 80 percentile. So it's above, in terms of, it's above average. And there's a few areas, some of the mountains, that's the concerning areas, some of our areas where we expect to see runoff, the snowpack, we're in that 90th or above percentile. So which means it's well above what we normally see since 1979. I've got other products that go back as further, but this is the one I've been using because this is one, it's nice because it shows the whole region. And so it's been a warm water year. And here's accumulated precipitation over the western Colorado. We use these areas, they're called climate divisions. So it's pretty much the whole western edge of Colorado, the accumulated precipitation over the water year. As you can see, the black line is the average. So it's actually not doing too bad in terms of total average, the total amount of accumulated precipitation. It's pretty much falling right along the average. We even had a few right around, let's see, October through December, it was a little above average, and we're kind of dipping a little bit below average right now. And if we go further south, well, actually southwest, northeastern Arizona, the climate division there in the eastern part of most of the Navajo reservation, below average, pretty much most all of the whole water year. Not a lot. It's not like the driest, but it's we're losing water, and in terms of not enough precipitation. And I'm going to talk a little bit about where all that water is going in a minute. So I just wanted to pick a couple, just one place actually. This is one of the high elevation snowtail sites it's just north of us here at the Stump Lakes. This is around 11,000 feet. And we have data going back to 1986 there. And so I basically put the green line there. I don't know if you can see. There we go. Nope, maybe not. Let me turn on I think I can do this. Laser pointer. Yeah, there we go. So this green line here, that's the actual accumulated precipitation starting in October, and then the normal is this line right here. So that's sort of the 30-year average. That's kind of we don't really get a normal year, but that's just if you just compare it to a long-term average. So by this time at that location, we should be getting right around 23 inches of total precipitation. Right now, we're sitting at 18.5. So we're below average. And then this bottom line here is the driest water year. And then this really faint blue line here, that's the wettest water year at this location. So we're sitting not in a really good position, but not terrible. This is just one location on the mountains in the basin. So as you can see, we've at this point in 1986, 87, we were at 37 inches, and it's not as bad as the 2001 and 2002, which is sort of one of the period of record worst case droughts in some parts of this. That was 8.8 inches. So we got 10 inches. We're above that, but still not good. So we've seen already some pictures, graphs of the hydrographs. These are just a couple points again. The one on the left is the San Juan River at Shiprock, and then on the right is the Animas at Farmington. It's small on my screen here. And so you can see that, we've, the blue squiggly line, that's the stream flow. And then the triangles is the long term. So we're sitting there below. And this one is I like to look at this one actually better because it shows the whole water year. And we get, this is from my colleague Stephanie, who's sits on our drought working group for New Mexico. She provides these kind of, where does it sit in terms of all the data bi-monthly, the discharge? And we're sitting there pretty dry. This is at the Animas stream gauge. I'm not sure which one, but okay, Animas River at Farmington. So that's one. We haven't put the main one on there yet. But yeah, we're sitting there pretty low. Not really low, but we start off pretty low and early in the water year. And as such, that kind of really, you can see that in the storage. I'll show both the Colorado storage. This is the lower basin over on the right side, and then the upper basin on the right side of the graph. We had some meetings the past few days with state of Arizona, and they were going through a lot of problems, as well as Southern Nevada, with the Lake Mead water restrictions, and dealing with not as much water because of water flowing a lot less in Lake Mead and Powell right now. So we know about those. If we go into a little further, little bit east of Rio Grande, the same kind of picture. Same trouble we're in. We've got a lot of users and a lot of water needed, but we don't have a lot to give. And so this is kind of the sign of our extended drought. We have some of my colleagues call it a mega drought, sort of defining that by more than 20 years, many decades, because we've been pretty dry over since 1998, 1999, and kind of seeing that decline, and kind of looking back, our 80s and 90s were late 70s and 80s were pretty wet. We're back down to that pretty dry phase here. So, I'll talk a bit more about what we think is causing that, but this is kind of where we are right now. We're I live down in Las Cruces, and a lot of the folks around with the Elephant Butte Irrigation District, there's a lot less to give this year. Only a few inches of water from the Rio. So with the reservoir right around 12, 11%, about right now. So pretty empty. And so, we use these tools like the U.S. Drought Monitor to gauge how bad is this drought. And this is this morning's, and it goes, remember, if you're not familiar with the Drought Monitor, it's not just a model, it's a multi-dimensional. We use not only models and observations, but impacts to gauge what drought is. And we have 4 different categories of drought, starting with D0, which is sort of like pre-drought, that's a yellow, and then going all the way to D4, which is exceptional drought. And we've got pretty much all of those in our Southwest area. And then in the basin that we're focusing in on today, it's mainly the D3, the extreme drought. And then even into Colorado, the basin, most all of Colorado, the Colorado River, as well as the Animas San Juan is in that same boat, D2, D3, going all the way into the main stem of the Colorado. As you can see that there. And so, a big chunk, which is about almost 16% of New Mexico is in the worst category of drought right now, is sharing that with parts of the Great Basin, as well as central Utah and the Southern Sierra. So this is something we're sharing a lot with the other states. And so this is a map that shows the change in that map over the water year. So it shows the number of classes. It's degraded. So if you look at some of the areas in eastern New Mexico, there's like a 5-class degradation. So it's gotten 5 classes worse since October of last year. And as you can see, that was kind of that pattern, that nationwide pattern, that would basically fits the pattern of a La Nina. It's basically the storm tracks dumping more precipitation on the higher latitude states. So along the Pacific Northwest going into the Northern Great Plains, more water, cooler storm tracks, dumping more precipitation, snow. I know I saw some social media posts, it's still snowing up there in some of the higher elevations in that part. And then as you go further south along the US-Mexico border into Florida, those are dry areas and sort of fits the pattern. And so it really does, we have some predictability, but it's sort of that sign of the times. You know, we've seen drought intensify much worse than we saw even through last year. And this is one of the most important graphs that I've been showing in the last couple of years. And it shows the impacts of where does the water go? So even though if you get a really good dump of rain, where does that water go? If it can go down and infiltrate into the soils, go into some shallow aquifer, the water cycle. But if there's a lot of evaporative power of the atmosphere, the thirst of the atmosphere, which is the evaporation as well as in the plants, the transpiration, that water goes right back into the atmosphere. So when we measure evapotranspiration, we look at the solar radiation, the temperature, humidity, as well as the winds. All those combined, and we've had a pretty windy season. I don't know about you guys. We had a pretty windy spring. It was ranked one of the windiest we've seen in a while. And as climatologists, we're still struggling to figure out what was going on to cause that. There's some theories, maybe some papers written on that in the future, but that is one of the important variables in the evaporation process. And this is one of the products I've been using a lot. It's called the Evaporative Demand Drought Index, and it's a gauge of the evaporative power, the thirst of the atmosphere to draw out the wick moisture out of both the soils and the plants. So it uses evapotranspiration estimates, and you can see the intensity, the most intense evaporative demand is right. We're focused in on the Southwest, and including the San Juan County, and even the La Plata and the far southwestern part of Colorado is not immune. It's in that, not as bad as you go further south, but it's pretty nasty in terms of the evaporative demand. And this is over a 60-day window, and you can see that. And so even if we get average precipitation, the water is lost quickly. Not all of it, but it's that the amount of water is wicked out quickly. And we've seen it. I've talked to a lot of ranchers in parts of New Mexico, and they kind of, it's sort of that feeling that, yeah, we've seen that. We've had a couple inches of rain, but it didn't stay around. Looking at the soil moisture, it's dry still, even with 2 inches of rain. So that's a real important part of this drought. It's a much warmer drought than the 50s drought. And so even the 50s drought were drier. The temperatures are actually making a much more impact than even the drying, less precipitation. And so we can see that in some of our products. This is a remote sensed view of soil moisture. And I wouldn't pay too much detail to the really big details here, but looking at more of the big picture of the browns and reds, where we're seeing that very similar area from that evaporative demand drought index overlaying on top of, kind of just looking at those two, it's the same areas where it's going into drying of the soil. This is down to the root zone. So it's the top meter of soil, seeing that. So that's it's an impact of the drought, is not only the high demand, thirst of the atmosphere, low soil, and then things like wind erosion. And this is something we've been looking at for several decades. Is if you in the high elevations in the San Juans, and as well as the Sangre de Cristo, we get dust on snow, and we've seen a lot of these events. So this is a satellite product that if the purple, the pink sort of that's dust being lofted off the ground and deposited at the higher elevation. So this was back in February 15th, and there was a more recent one, pretty nasty dust event. You all probably know about this because if you're living in this area, this was just recently May 2nd. And that dust is kind of pushed off. Southwesterly flow, very intense. There's been some other, the trough has moved in and is blowing the dust toward the southeast, but these are the ones that brings the brown snow in the mountains. And I talked to some of the folks over at Silverton about that, and they've been taking measurements of the snow and how it's impacting and quickening the melt out of the snowpack because of the dust. So it's a positive feedback thing. That basically it's hastening quicker melt out, less water, creating this cycle of making it more arid. That's sort of one of those things that we're looking at over time. And we've seen these pop up when there's drought years, La Nina. We get a lot of these dust events, and not only New Mexico but also in little Colorado area in Arizona. So these are kind of the sign of the indicator of drought impacts. So I want to kind of give you some information about what we're looking at in terms of the forecast outlooks. We call them more outlooks. They're not really forecasts, but we looking at, so what phase of the El Nino Southern Oscillation are we looking at toward the end, after the monsoon, what's kind of lying ahead. So these are the bars that show the probabilities, and you probably can't see the dates on here, but we're in this April, May, June, and May, June, July, June, July, August, September. So here's our summertime here. Here's our winter time over here. And so we're in this blue bar, which is the La Nina. So right now we're in a La Nina. So it's 100% probability. As we go further in the monsoon, the probability goes down, but it stays pretty high. The gray is the probability of a neutral ENSO. And then what we want to see is this red bar pop up, but it's pretty low probability. That's a El Nino. Those are usually, we want to see those because for our area, it's usually cooler and wetter, more snow, but it's a fight between this, right now it's a dual, it's a fight between the El Nino, La Ninas and neutrals for next winter. It's still too early to say, but it's not like, this is our third one. This would be the third one if we got this La Nina to come back again. So there's been some in the past where we had 3 in a row, and they weren't very pretty in terms of the snow. But so it's something to keep an eye out on is for this. This doesn't really, there has no power of forecasting the monsoon, unfortunately. It's mainly on the winter snowpack. So this graph is mainly just as an aid to show what's going on for the cool season. Doesn't really help us. However, we do have some inkling for the monsoon, which is my good news for today. I gave it the bad news first. And so the good news, this is as of midnight last night, the forecast for rain for the next 7 days. And this is looking at going all the way out to next Thursday. And so wherever you see the blue and dark greens, that's precip. And so the blues is like about an inch. So the nice thing about it is I've been looking at this moisture coming in. It's over in the over the Sierra Madres right now. That's at least in terms of the northern Mexico. It's right on the mountain boundary between Chihuahua and Sonora. We're watching this pulse of moisture come in, and I was just watching this, and I was looking at some of the forecast models this morning, and it's like, yeah, there's a high pressure sitting over us, and it's forecasted to move east, and that's kind of what we want. And remember, the highs draw air at the lower levels in a clockwise, and then there's a low that's going to be popping in, coming in from the Pacific, coming in from the west. Remember, lows they go counterclockwise. You can kind of see that kind of like gears moving at and in lower levels. So, which if you get them timed just right and spatially, they can draw moisture or whatever air is that's parked between the two highs and lows, and we can see that. So our hope is that we can dip into that. If highs and lows can be positioned right, we can draw some of that moisture in. So that's kind of that's our hope, and that's about next week. That's probably right around next weekend. So we'll see. I really I got my thumbs up because I'm really hoping to see that, because that will be a little early monsoon. It's comes right in on time. We really need it, of course, but it's like, yeah, we usually can see them coming in right around the middle of June. It's usually haven't seen them that early, but and it's, you know, not for this area yet, but for southern New Mexico and then southeastern Arizona. We're waiting to see what the pattern shows, how long that low. It depends on if it's a stationary low, or does it move off really quickly? Then if that moves off fairly quickly, then we may be drawing some of the continental drier air in. So we don't want that, which basically and then that may drift the high back. Whenever the highs are the subsiding air, the hot, you know, we're expecting over 100 degrees in southern New Mexico, and that's that subsiding hot air. That inhibits storm development, dries out the column. But if we can have that system parked there, that's our hope. And that's our what we want to see in the forecast. That's kind of what I'm looking at every day, is where are the positions of the highs and lows. We don't want it to be too far west. So in terms of that, the official forecast, this is as of this morning, is basically the 8 to 14 day outlook. This is what I've been focusing on. This is kind of a great news because that's the probably higher chance of above average precipitation for the Southwest. And it includes most of Colorado as well. So that's good. And if you go further on the rest of the summer, that sticks around. That above average chances is here. And not as good for these guys. There's drying. So, but the white is good. It can go either way. So in terms of probabilities, so this is that's my good news. We don't have any more details other than this is what it looks like. You know, it's kind of it's a regional forecast. It's not specific for the watershed or even a county. We don't have that predictable power. We have models out there, but they can go different directions. So we don't want to mislead anybody by showing that much detail, but we want to show that the monsoon is coming. It's already down in Mexico right now, watching it come in. So, however, we are still kind of remind ourselves, we are still in a long-term drought. And even if we get a really bang up monsoon, we have deficits in precipitation and warm temperatures. We can go back to that. This guy here, above average temperatures, even with the monsoon, we have really warm temperatures. So that's why we have in this map, the chocolate brown is basically the Climate Prediction Center saying that drought is still going to persist even with a healthy monsoon. It's going to help, of course, we get green up, but in terms of defining drought as, you know, the deficit of precipitation, we have impacts, we have less water in reservoirs. That's not going to go at, that's going to be still with us, but we have got some short-term good news and you know, especially down in southern Arizona in this part, but we're still looking for some good precip and runoff. You know, that's good. You know, green up. I saw some precip yesterday on my drive up from Las Cruces. There was some good thunderstorms out there. Last few slides I want to show is, you know, the longer term outlook. You know, these are more generalized. You know, we're seeing this trend of warming over the four corners, all of the different, these are the boundaries of those black lines, those are the climate divisions. So, you know, in the southeast corner, that's New Mexico, 0.6 to 0.7 degree rise in temperature, average temperature per decade. So that's the decadal increase. And if you draw a line through the annual average temperatures and pretty much all the four corners climate divisions are showing at least a 0.6 degree Fahrenheit increase per decade. And this just particularly, this is June, July, August, but you can look at other time periods very similar. And so this is our time period of putting it all into context, going all the way back to 1895. This is the Western Colorado Climate Division, the average annual temperatures. And this is the climbing, that 0.6 degree Fahrenheit per decade. That's that line right here. And so 2017 was our warmest year. Last year was the third warmest. So we're seeing that even though it was, and even though we got some cooler years, but still, we're well above the century average. This is the black line here. So I just picked one of our ensemble models that I typically been using. We use the same one for our 50-year water plan for the Interstate Stream Commission. I just moved the model prediction a little further north into La Plata County. And basically this is kind of what it shows. And these are this dashed line is the 1950 to 2005 average temperature. And these are the different scenarios, the lower emission and the higher emission. So it's by these, looking at the window out to 2040, it's at least a 2.3 degree increase to 3 degree. And then if you go out to 2070, it's a 3.9 to 6 degree increase compared to that 1950 to 2005 average. So, we're seeing that warming heading that direction. So that previous graph I've showed with the map of the 0.6, that's expected to continue to climb. So, I'm not trying to make it look negative, but it's more of it. So how do we adapt to these kind of things? This is kind of the broken record as climate scientists and climate service people. We're saying, how do we deal, not think about how bad these are, but what are the things that we need to do to become more resilient, to adapt to these things, declines, less water, changing the snow, earlier snow melts. How do we deal with that? Where do we do what? We got to think it out of the box and you can't just think of things we've done in the past. We got to think about what about this? There's no crazy ideas. We need more monitoring to know how bad it is and where do we need to focus our efforts on. And, I just picked one slide on impacts to agriculture, having, knowing that there's more evaporation of ET, stress on plants. So what are maybe our, in terms of choices on forage feedstocks, what can we think about there? And, thinking about forage quality with less water, what kind of studies, where do we need to bring in, maybe animals, dealing with, range, are there better areas to range and how do we manage those? And then dealing with costs, because it's, during drought, it always costs more if you're going to keep up the the animal numbers. A lot of the folks I've talked to have reduced their herds, and they haven't really brought them back up even after a really good monsoon. So it's managing that. And so there's lots of things that we need to think about. It's not all negative. It's more of making opportunities and adapting to these and kind of moving forward and thinking about, okay, I can do this. Here's what we need to do. And working together. We had 2 meetings this week. It was a drought learning network. And I encourage you, if you're interested in this topic of thinking out of the box and learning from each other, there's a drought learning network that's going on right now. There's like 5 different groups dealing with tribal efforts, people to people. There's monitoring. There's different things, and it's open to join and to kind of work together and to give ideas, and that's how we're going to solve some of these. Becoming more resilient is to work together. So, and then want to give you one opportunity to help with the climate part. And it's helping us measure precipitation through a citizen science, or we call them community science is more better idea, a name for it. And this one I've been helped run is called COCORAS. It's Community Collaborative Rain, Hail, and Snow Network. And we do precipitation, so rain, hail, and snow. And so there's pictures there of the different things we measure. And all you have to do, here's a rain, hail, and snow. And there we go. The tools that we use are rain gauge and the internet. So most people have a cell phone who can go online. So if you have one of those, you can do this. And it's getting one of those plastic rain gauges that we have for Kokoraz. It's about $40. All you have to do is set it up, get trained up. There's some online training and you're ready to go. You can help us out. We need a lot more observation because we need to know where it hasn't rained. Because we know there's some efforts to get some radars in Colorado. But it's still, those are ongoing and we need to know how much actually has rained. We don't really know. The radar from Albuquerque is really not sufficient. There's many times I've been here, it's pouring rain and I look at the Albuquerque radar and there's nothing. It's like it totally missed that whole storm. And I was like, I tweeted it out to the Albuquerque office and said, yeah, I know. You have to have gauges. You have to have gauges in order to get that. The additional radars are great, but it still won't cover the entire area that's not covered. It's looking at, the current radars look at like 10,000 feet. But we need to have those gauges here for the, the folks like the River Forecast Center. They use that to kind of to gauge, to calibrate some of the radar. These are critical right now. And so, I just picked one random time in the past during the end of the monsoon a couple of years ago. These are observers, people like you and me, neighbors, friends, family, taking measurements. This goes into the national database, goes into models, this goes into predictions. So it's not just for fun or just a scientific curiosity, it's operations. And so I encourage you to, if you're interested, go to that website. They're kokoraz.org. And I totally blew it. I should have brought brochures, but if you can write that down, if you're interested in Kokoraz, COCORAHS.org. And there, I think I'll stop there. So I think I'm probably right about time. So any questions? Yep.
You showed that one where the winds are coming from the southwest, one to the. You showed the winds going from the southwest to the northeast. If you look at the soil mass, there's a sand level. All the sand dunes, sandier soils, north, the southwest, northeast. And that's the soil. Geologists call it dirt, but it's soil. Surface things, though.
Yeah.
It's theirs.
Yeah, absolutely. Yeah, we see, especially like with the radar, we see these kind of where the rain has fallen. And a lot of times it's along those paths, the preferred wind direction of the synoptic wind flow. And, that's our predominant winds is southwest, it seasonally changes, but it's on average. Yeah.
And they've been there for thousands of years.
Yep, exactly. Yeah. Yep. Good point. Yeah. Question.
With a dropper system, they're going to put around Durango, help the city.
It will, yes. In terms of, the question was, will the new Doppler radar is going in help out? And the answer is yes, that definitely. And I know the Weather Service, they're the primary users. So it's more of knowing how much rain has fallen as well as warnings. When we get thunderstorms, get these microbursts, be able to predict those and knowing where those are falling. And, these radars are great, but we still need the rain gauges, what's actually fallen on the ground. That's still important. Even, as soon as you get away from the radar, the beams goes out. So farther you are from the radar, it doesn't really see the ground. So especially when we get low level dry air, you can get virga. Rain falls into about a couple thousand feet. And then in the bottom, 1,000 feet or so, it could, that number can go way down in terms of the evaporation. Then you get wind. The energy goes from somewhere. It goes from evaporation to wind, and we get those. But radars will definitely help. Yeah. You good? One more.
Probably I would say, we're quite a bit over time, so I
Oh,
would say,
sorry.
will you be available for questions afterwards?
Yeah, a
for
few
anyone?
minutes. Yeah.
Okay,
Yeah, thanks.
all right. Thank you so much, Dr. Dubois. Thank you. All right, thank you. So no worries, so we'll just we'll adjust our schedule. We'll allow our remaining presenters to keep their set presentation times of 30 minutes for the remainder of the afternoon. So with that, I will introduce our next presentation from Susan Beharry. Susan is a hydraulic engineer with 17 years of experience with water in the West. She's been with Reclamation since 2012, operating Navajo Dam, a Colorado River storage project unit, as well as providing modeling and operational support for 5 other reclamation projects in the San Juan Basin. She works closely with the San Juan River Basin Recovery Implementation Program with the shared goal of recovering endangered species in the basin while managing continued water development. Susan earned her master's degree at Colorado State University in 2005, and she is a professional engineer licensed in the state of Washington. Welcome, Susan.
Right. Well, hi, and thanks for having me. You know, what's funny is 20 years ago, I'm going to click this pen the whole time. You guys are just going to hear it because I haven't given a lot of in-person presentations in the last 2 years because of COVID. So now when I give in-person presentations, I click a pen like the whole time. So, you know, if it gets annoying, just tell me. So 20 years ago, I was at Colorado State University and I was a physics student and I was trying to find something else to do with my time, some part-time job. And I got a job with the assistant state climatologist at the time, Nolan Duskin, who was starting this grassroots little startup called Kokoraz, which you just heard a whole bunch about. And it was me and one other student, and we would sit there and we would cover these foam pads with foil, little hail pads, we called them. And, you know, we'd send them out to people on the eastern slope. At the time, it was called the Colorado Collaborative Rain and Health Study. And now it's the Community Collaborative because it's all over. It's in Canada. It's amazing. I can't believe how big it's gotten. So really good program. Just wanted to give a plug for that. And you know, I was there at the start, you know. So anyways, yeah, Susan Beharry. I worked for the Bureau of Reclamation. I've been with Reclamation for about 10 years doing operations at the Navajo unit. I also do flow and operational forecasting for the other reservoirs. So my talk is going to be about just generally how Navajo unit operates. I'm just going to kind of do an overview of that in case anybody isn't real familiar with what we do or how we operate it. And then I'll talk about just the challenges and issues that we're facing with really a lot of the stuff that ties into Mr. Dubois' talk that he just gave. So this is just a quick update on, or not update, this is a quick summary of the Colorado River Storage Project. The Navajo unit is one part of a very large system called the Colorado River Storage Project. We call it CRSP. So it was authorized in 1956, and it was mainly to provide flood control, irrigation water, and also to control flows that go to Powell for power production. So Powell is one of the initial CRSP units, along with Navajo, the Aspinall unit in Colorado, and the Flaming Gorge unit in Utah. So together they work as a system, they work together. The power revenues that come from these hydropower units are fed back to Reclamation to help pay for the you know, parts of the CRSP Act maintenance and also things like recovery program. So if there's any endangered species recovery issues, then a lot of the power from the hydropower, or a lot of the funds from the hydropower come back and help fund that. So it's really important. That being said, Navajo doesn't actually produce any federal power. So Navajo does get federal power funds, but it produces private power. So the unit was constructed in 1963, holds about 1.7 million acre feet. And even though we have 1.7 million acre feet in there, we can only actually access about 1 million acre feet just because of elevations in the reservoir. And I mentioned, but Navajo unit was authorized for irrigation water for the Navajo Indian Irrigation Project. There's other contractors that have water stored in Navajo, the Jicarilla. There's some smaller contractors as well, but mostly Navajo's purpose is to fulfill these water contracts to the Navajos, to the Jicarilla, and also to release water down to Powell that is timed in a way to benefit endangered species. But there's benefits on the side that are not part of the authorized purpose. There's a really amazing fishery downstream, I'm sure everybody knows about. People raft on the San Juan River all the time. There's lake recreation, and there's also private power production. But none of those things, while they are benefits, they're side benefits, or they're benefits of the project, the operations of the project are not in order to benefit those things. Those just happen to be benefits. We don't make operational changes for lake recreation, for example. And the way that Navajo is operated is through a record of decision. Reclamation puts out a record of decision to just basically state, you know, we have assessed all of these different alternatives. We have consulted with different stakeholders and tribes and federal agencies, and this is how this project will be operated. So the record of decision for Navajo says that we will try to meet these endangered species flow goals. We're going to try to target these flow goals while also providing water to the contract water users. And what that looks like is basically two main operations that we do. A spring peak release, which you probably haven't seen in a long time because there hasn't been enough water in a very long time to really do a spring peak release. But let it be known, we have done spring peak releases before. I think the last large one was in 2017. We did 2016 and 2017. We did a very short one in 2019. But other than that, you know, ideally we would be doing one every year. And a spring peak release would be mimicking this natural snow melt that comes off and combines with the Animas to create large flows downstream for the endangered species. And then the other operation we do is maintaining minimum base flows for the endangered fish. And the endangered critical habitat is from Farmington, just downstream of the Animas confluence, all the way to Lake Powell. So we are trying to meet endangered species flow targets with the water that we have to send down. We have to send it down anyway. It's water that's part of the CRSP system, but we time it in a way to benefit these endangered species. So that's where the spring peak release comes from. And so what does that usually look like? I have two slides in a wet year and a dry year. And the wet year, you might not even recognize it, but in a wet year, we might have really good carryover storage. We might be able to make really, really low releases in the summer because the Animas is really pumping and, you know, people are irrigating, but the Animas is taking care of most of it. So not a whole lot of water has to come out of Navajo. And we might also do this large spring peak release like you see. This was 2005. In a dry year, which is much more common now, we might be making really high releases in the summer. The Animas goes to zero. The Animas River in Farmington, sometimes it just completely dries up. And so everything that comes out of the dam is intended to be meeting this endangered species flow goal, which is on top of all the irrigation that's happening in the system. So in a really dry year, we might have really low carryover storage. We're making very high base flow releases, and we don't have a spring peak release. So those are sort of the two ways that you can look at how our operations are. And this second one is much more typical for recent years. This was 2018. So the benefits of these releases outside of just meeting Endangered Species Act goals, like I mentioned, are we're trying to maintain channel capacity for dam safety. Even though we have had a lot of dry years, you can have one very, very wet year and fill or even potentially have to spill the reservoir. So we need to always maintain channel capacity downstream of the dam. And what happens around here is, you know, New Mexico soils are just full of sediment. Southern Colorado is full of sediment. Anytime we have a monsoonal event, a lot of sediment comes into the channel and just kind of packs it full and makes it so that the capacity decreases basically. So we need to routinely be flushing some nice, clean, clear water out of the dam to clean this sediment out. But like I said, we haven't had the water for that. So the operational tools we use for all of this is, I'm just going to mention some forecasting. We work really closely with the Colorado Basin River Forecast Center. They're in Salt Lake City, and they provide forecasts for all of the different river basins. They tell us on a daily basis what the update is for how much water they think is going to come in. And they give us a big range. And so we try to look at those high ends and those low ends and the middle range and determine how would we operate under these scenarios. And as we move through the year, it narrows down. We do a lot of modeling with Riverware modeling software. We do coordination and collaboration with many different federal agencies, state agencies, locals, tribes. We do stakeholder meetings 4 times a year, or 3 times a year, excuse me, where we meet with all the stakeholders and we talk about what we think we're going to do, try to get feedback. Those are open to the public, so if anybody ever is interested, you can attend those. Now I'm going to kind of try to talk about some of the issues and challenges we're facing. I'm going to just touch on modeling really quick. I'm not going to try to explain modeling or get really into the weeds or boring. I'm just going to try to talk about the fact that we use a lot of different types of tools in order to get different answers. This is just an example of 3 of the models that we have where we try to determine what our operations are going to be. And this is not just for Navajo, this is for the whole Colorado River system. When we're talking about just short-term planning, we might just try to come up with a solution, one solution for how we're going to operate this year. And that's what we call this first deterministic model. That means that we put in one set of forecasts and then we have one set of operations and we go with it. And that might work for the next week or 2. Then as we move out into longer term planning, all the way to the end, the CRSS, Colorado River Simulation System. When you see those plots like you just saw in the last talk that show this kind of shaded gray, range of possibilities, we're doing this kind of probabilistic modeling where we run 50, 100 different potential operations to kind of come up with, possibilities. And I'm mentioning this and I'm talking about this because when we talk about climate change, there is no one answer that we're going to get. There's no, this is how it's going to be. We have this enormous range that almost feels overwhelming. What do we even do with this information, right? It could be nothing or it could be huge. What do you do with it? So we run it through these statistical models to determine the likelihoods of different operations based on what we're seeing for these climate change inputs. So the challenges that we're seeing, right now on a more local scale, Navajo specific San Juan Basin. When I talk about the San Juan Basin, I'm talking a lot of times about the snowpack. So that's going to be southern Colorado. We're seeing obviously reduced hydrology. We're also seeing dwindling storage at the reservoirs every year. And the Animas flows are also dwindling. So really all of this stuff is sort of, obviously going down. But the interesting thing is we're also seeing changing precipitation phase. So instead of everything falling as snow, now in this early winter and late winter, we're seeing it fall as rain. That doesn't get saved in the reservoir bank of snowpack way up in the mountains, right? That just comes right down, comes down the river, goes all the way downstream to the next state, and nobody's irrigating because nobody's using it, right? So we have to use more water from storage during irrigation season then. So changing precipitation phase, the warming climate that is making that happen is also a really significant, has a significant effect. We're seeing early runoff. We're seeing dust on snow like we just saw about in the previous talk. So we're putting a lot of dollars into forecasting tools. This is how we're kind of looking at this, reclamation is. And we're putting a lot of money into these tools to determine how much is irrigation going to increase? How are we going to basically do more with less? And that's where we have this drought contingency planning. This is an example of just a really long-term tree ring reconstruction of hydrology. for the San Juan River. This kind of black, and maybe that works. This kind of blue line here, I just drew that in, but it's showing the average. It wasn't populating right there because this study was ended in 2000. And after 2000, from 2000 to 2020, this is the average at that gauge. So we're definitely in one of the lower, the lower echelons of the long term, not just in the last 50 years, but in the long term reconstruction. And this is soil moisture saturation at Lizard Head Pass. I'm not going to talk about all this a lot because this was covered in the last talk, but just kind of a example of how we can actually physically see the soil moisture just disappearing and how quickly it happens. This is soil saturation at Lizard Head Pass, and it starts in 2012 and it goes through 2021. And every time we have a little bit of snow melt runoff, I'm sorry that I could do both if I had two. Every time we have a little bit of snow melt runoff, the soil saturation suddenly turns blue. It's just, really exciting. But in order to keep that soil moisture blue, you have to have a monsoon season. And that's really the thing that we're not paying as much attention to, or we are now, but we haven't in the past, is the fact that we really need those replenishing rains in the summer, or else we just lose, we just lose all of our soil moisture. This is, I took my son up Ophir Pass after one of those. It was actually the second graphic that Mr. Dubois showed of the dust event. That second one that just looked really massive. I took my son up Ophir Pass, and amazingly, you could drive up there already. It was, I think, early April. So you could already drive your car up to the very top. And it almost looked like, in this bottom central picture, it looked like he was walking across almost dirt and leaving, white snow footprints instead of the opposite. It was just astonishing. And the rapidity with which everything just ran off so quickly, the momentum that the snowpack gained from this dust, these dust events. We tracked 8 dust events this last year. It was just incredible. And it makes a really big difference. If we have early runoff, dust creates early runoff. If we have early runoff, the ground warms up earlier. We had a month early runoff. We have a month of extra dirt to sky FaceTime where the soils are really warming up, and it's just exacerbating the problem, obviously. So in addition to not really having the infrastructure to capture these events that are changing precipitation phase, when they run off really early, we also don't have the ability to we don't have the ability to capture these really early runoff events, basically, because that's not when traditional irrigation is happening. That's not when we want to use the water downstream of the dam, if that makes sense. I'm not going to talk about climate change specifically. I think that was covered really, really well in the last talk, but reclamation, we conduct a lot of planning studies on climate change because it is obviously going to be one of the big drivers in our operations in the future, with the big question of, we're having less water. It's in this weird phase that isn't something that we're used to in the past. How do we do more with less? Well, all the climate change studies, they talk about, in 200 years in the future, it's going to look like this. But for operations, for dams and reservoirs, we need to look very specifically at what is it going to look like in the next 50 years while we're restructuring our infrastructure, and how does that compare to basically what we've seen from the 70s to now. So we've done very specific studies on how it would affect specifically operations. And I put a link on here if you want to look at, we have something called a drought. It's called the Addressing Drought Portal. And I think that's the link right there. It's kind of a long link, but if you also go to the reclamation website, you can look through it. So we have a whole lot of studies going on. We have these basin studies. I'm sure a lot of you have heard of the bipartisan infrastructure law investment. So this is $8.3 billion for reclamation water infrastructure and 2.5 billion for authorized water rights settlements. So that's going to be something that's really starting to be developed in the future, in the coming years. I think we're going to be hearing a lot about that. Things like, projects that will help us not only improve the infrastructure that's already there, but make it so that it's a little more water efficient. We also have these drought response programs. Any applicant who wants to develop a drought response program can come to Reclamation, and we provide funds to help them put together planning and how are you going to survive a drought at this level? What are the uncertainties that you have? And how can Reclamation help to shore up these plans? We have those. We also do a lot of work with the one thing that we can control at Reclamation is reservoir operations. We can't control the weather, and we can't really control water usage. We can provide money to help make water usage efficient, but we can't control anything beyond that. So reservoir operation efficiency optimization is really, really a big part of what I do. It's trying to figure out how can we meet all these needs when we only have this level of water. And a lot of times it comes down to timing or what I would call maybe flexibilities within the operations, do something one year and not the next. We're also working really hard on improving our planning and modeling. We're only as good as our forecasts, and developing best practices. So we communicate a lot throughout the basin with the other operators, with the other reservoir, with the other basins, and try to determine, have you been through these problems? Every 5 years, we put out the Secure Water Act report, and it analyzes all the risks that we are aware of to projected risks to water supplies. And we highlight our collaborative efforts to try to mitigate those risks. So this is an actionable thing that we can take and start working off of. And then I talked about this a minute ago, but we've collaborated with the Desert Research Institute, DRI, and the University of Idaho, and we come up with these modeling tools that tell us in the future how much worse is irrigation going to have it than currently, or in the past, or what we've seen in the 70s and the 80s and the 90s. How much water is it going to take? How much ET is it going to take to grow the same crops or to grow different acreages? And this graphic at the top left is another depiction of a dust layer. I got that from the Center for Snow and Avalanche Studies. We work pretty closely with them to track the dust and the snow. The picture that I showed of my son that was on the CSAS website, felt he was famous. Famous 3 people. Then we also work really closely with the NASA Airborne Snow Observatory. They're doing some great work trying to get now it's just the Airborne Snow Observatory, but they're trying to get a handle on basically a spatial coverage of the snowpack at one time. So when we have snow tells, we have a full temporal range of coverage of snowpack through. We have a temporal snowpack coverage, so that means that it's taking data every single day, but it's only at single points, right? So it's not necessarily a good estimate on its own of what all the snow that's up there, because we only have these few SNOTEL stations, and the Airborne Snow Observatory will take a snapshot of everything, a complete coverage of the entire basin, but at one point in time, because they're just doing that flight once. So combining those two sets of data together can give us a much more complete picture of how much snowpack is actually up there. And then the last thing you'll see on this bottom of this slide is the drought contingency plan. It was signed in 2019 in an effort to prepare the basin for what could possibly be really, really low water conditions, not just at the reservoirs up here, but also at Lake Powell. And I'm sure a lot of you have heard that time has come quite a bit sooner than we were all hoping, but not necessarily unexpected. So now the upper initial units are sending water down to Lake Powell in order to help them continue to produce hydropower. Because as I mentioned before, those 4 initial units were built as a system. So, so water from Navajo has not been sent down to Lake Powell, and there are no plans to do it at the moment because of really low storage levels at Navajo. But if situation improves at Lake Powell, then hopefully that won't be an issue that we have to really consider. But in May of 2022, 2 drought response actions were announced from the Upper Basin. One's called the 2022 plan. That's where 500,000 acre feet are being sent down to Powell from Flaming Gorge. And then the Glen Canyon operational adjustment, in which about the same amount is being held back in Lake Powell and not being sent downstream to Mean, for a total of just under 1 million acre feet. So while these actions do reduce the risk of Powell fouling below minimum power pool, there's no certainty. We do have these documents that lay out the plan for this year, and it's at that link that you see at the bottom. So right there. So that's pretty much all I have. And I covered a very wide variety of topics, from Navajo operations to climate change, to my son, to Powell. If you have any questions, I'd be glad to answer them. Good. Great. Okay.
Given that so much of Mexico's available water supply evaporates from reservoirs, I was wondering, it's not managed our better way to manage water. I was just wondering what your estimation is thinking about managed aquifers and storing water around the lakes and all that.
Yeah, evaporation is a huge problem, and I have not heard of reclamation talking about doing managed aquifers at all. But I think it's just because that might not be in our specific wheelhouse. We have basically surface water projects. So but I think that we are definitely working on at our technical service center and our research development center, we are working on a variety of tools and methods to reduce evaporation. But I don't think any of them are very far along. So I think it's going to continue to be a pretty big problem from the dam perspective.
Well, we need to change the law or policy.
Yeah, every
Your reclamation will work.
Yeah. Yeah, I mean, it's a really good question. I don't know that I have the answer on that, but I think that as we do continue to lose more water, it's going to be very, very obvious. I mean, it's obvious to us now that a lot of it comes from evaporation, but I think that that complete overhaul of infrastructure, I think that reclamation is tackling some more low-hanging fruit first, but that doesn't mean it's out of the question.
Lake Horse loses about 3,500 acre feet a year to evaporation. Do you have, off the top of your head, estimate of Navajo evaporation loss?
I think it's about 30,000. Yeah, it's quite a lot more, obviously. Yeah. It depends on where, I mean, that's recently because, if we had a full reservoir, it's a lot different than if we have a halfway full reservoir. It's a lot, especially as it gets hotter and warmer and windier. Yeah.
Speaking of Lake Neighbors, is there been any investigation of using that as a pump storage facility?
Not to my knowledge. pump storage facility? What do you?
For power generation, you know.
Oh, like have power at the outlet?
Yeah, so you have peaking power, pump it up at night,
Yeah,
and it's low, and then run it back through.
yeah, there actually was some talk of putting in a power plant at the base of it, and I don't really know the details of why they didn't do that, except for that because it never releases in the early, right now, we're not, making any releases. I think they just didn't put the effort into putting it in. And also the release is fairly low. Even if it was releasing at a high, at its full capacity, I think that the numbers just didn't work out.
Thank you, thank you.
I don't think that that means it couldn't be put in the future if it became apparent that it was useful.
The NASA airplane, if the whole picture, but you can't get that from space, from the satellites. It's not accurate enough.
No, they use special LiDAR, the specific kind of LiDAR that needs to be a lot closer. And yeah, it's to get the resolution and everything, they're flying it from a pretty low flying plane. Yeah. Okay. Thank you.
Thank you. I know there may have been some more questions, but I encourage you, those of you who didn't have the chance to ask questions of Susan, she'll be sticking around for a little bit. So if you can catch her before she leaves, you can ask your question then. Thank you. All right. Well, I'm incredibly honored that our next speaker was able to take some time to share some remarks for those of us attending here at San Juan College, as well as for those attending on Zoom as well. Congresswoman Teresa Leger Fernandez represents New Mexico's 3rd Congressional District. In Washington, she holds a leadership role with the Congressional Hispanic Caucus as freshman representative. Congresswoman Leger Fernandez serves as chair of the Subcommittee for Indigenous Peoples of the United States for the 117th Congress. She has also been appointed to the House Committee on Education and Labor, the House Committee on Natural Resources, and the Committee on House Administration. She is a 17th generation Northern New Mexican. Before coming to Congress, Leger Fernandez worked as an attorney and advocate and won important legal battles to advocate voting rights, promote tribal sovereignty, and protect our environment and Acequia waters. Thank you, Congresswoman.
This is a fascinating conference. You don't know, this is the kind of stuff that I start kind of geeking out on. I was reading all of the papers and the posters and saying, oh my God, we got to follow up on this and we got to follow up on that. But I'm Teresa Leger Fernandez, representing my beautiful and beautifully diverse 3rd Congressional District, which has not just the wonderful city of Farmington and Aztec and Bloomfield, but going all the way over right now to Clovis and Portales. I have 16 Pueblos, the Jicarilla Apache Nation, and the Navajo Nation in my district. And I can tell you that there is no place, not a single square inch of space in my district that doesn't have huge concerns about water. And so what you're doing here today to talk about how do we manage our water, how do we look at the ecosystem, how do we follow those graphs so we have a little more blue on the soil is of utmost importance to everybody in my district. And it's of the utmost importance to everybody in the Western United States, right? This is what you guys are talking about today is essential for as we move forward, and whether it is that we're going to start looking at something we might not have thought enough about before, but need to consider, like storage, or what do we do with that water? Let's make as much use of it. I just came from the Cutter Lateral celebration, which, as you all know, the Gallup Navajo pipeline and project is operational in many places. Cutter Lateral is one of those where there was indeed the ability to have water to the Navajo Nation chapter houses and areas. And thank heaven there was, right? And because those areas, we all suffered so such loss at the beginning of the pandemic, but those places at the very least had water. And so, that is something that I think is really important. Before I got to Congress, I was actually an acequia commissioner, as was mentioned. So, it was my job to work to make sure that we protected those acequia waters, those irrigation waters. We shared them equally, that we protected them from, developers who just wanted to take them out of our system, which would have killed us in terms of our ability. And I still, while I'm no longer a commissioner, because this is a full-time job, I still am a paciente, which means that, I have water rights on several acequias, which are in the Pecos and along the Guaymas River. And as you can imagine, my heart is broken because the memories, the places of where my happiest memories are now consumed in ashes. And we are going to have to be doing a lot of work everywhere to talk about how do we make ourselves more resilient? How do we work on our forests so that we do not have catastrophic wildfires and it's not too late? And I think that that's the key thing. And what I've been very pleased about what I've been able to do since I got, I'm a freshman congresswoman. I've only been there about 17 months, but we have focused on the things that I think are important for the issues that you're talking about here in today. And that is that making sure that through the bipartisan infrastructure bill, we put the money that is necessary to work in partnership, both in when we're talking about forested watershed, the good neighbor policies, work in partnership so that we can protect those watersheds and hopefully including prescribed burns, but not prescribed burns during the windiest month of the year in New Mexico. But we have a lot of money in there that we will be good. We also, I put together this. I love this thing. I started reading it right away. But I put together a little summary of delivering for rural New Mexico, the Infrastructure and Jobs Act rural investment. I'll leave a couple of copies here, but this is available on my website, which summarizes some of the funds that are available. I wanted everybody to know what were the kinds of funds that were available in terms of building that resilience, in terms of getting clean drinking water, in terms of getting that water to the farmers and ranchers when they need it. And so I'll leave this here. You go to my website at fernandez.house.gov, my official website. It lists some of those funds that are available. I'm also really pleased that I've been able to address the issues around, it's my understanding that this conference kind of came out of, maybe I'm understanding it wrong, but came out of the Gold King mine, right? And so I do recognize that the federal government has to be accountable for that, right? It is interesting that my job is not just about making sure we send resources where we needed, like we've done in the bipartisan infrastructure law, but also that when government messes up, kind word, right? They blow it, that we must hold government accountable. I'm doing that with regards to the Hermit's Peak Fire Assistance Act, because we must hold government accountable, because we are destroying lots of watersheds up there and we don't yet know. We are going to just have to put on steroids. Maybe I shouldn't use the word steroids because it's not a good thing to be on steroids, but really, really work really hard to figure out what do we do to protect that watershed. The president will be coming to New Mexico to hear some of the work we're doing so that he understands what our needs are. He has acted quickly, but my Hermit's Peak Fire Assistance is to say FEMA is not enough. We need to make sure everybody is compensated for their loss. That is the same approach I take to the Gold King mine. And so with the Gold King mine, I have authored and I have pushed the Department of Justice to start looking at entering into settlement with the individuals, farmers and ranchers who were harmed. We know they have entered into the settlement with the state of New Mexico and with the Navajo Nation, but that's not enough. There were a lot of individuals who were harmed, and I am pushing that they enter into those settlement agreements. I also suggest that because many of those ranchers and farmers or out at chapter houses, that they place the claim settlement processes in the chapter houses, right, where the people are. Because I think that's really important, that our government needs to show up when it's time for us to be held accountable, but we need to show up where the people are. I want FEMA to be in Mora and not in Santa Fe. I want when we hopefully get the Department of Justice showing up and resolving those claims, I want them to do it where the people are. I've spoken a little bit, and our prior speaker mentioned some of the pieces that are in this bipartisan infrastructure law. I'm really pleased that it does contain $21 billion to clean up Superfund and brownfield sites, abandoned mine land, including funding based on my legislation that I did for orphan RALs, because I authored my Orphan RALs and Jobs Act, which was intended to clean up the orphan RALs. I'm really pleased to report that we got $4.7 billion in the Bipartisan Infrastructure Act to do that cleanup of the orphan RALs, because those also, we're talking mostly about stream water right here, surface water, but we also need to protect our groundwater and our aquifers. So that's something else that I've really pushed on. And then the ecosystem restoration, there was like $8 billion in general for lots of the water work, but we also recognize that this ecosystem restoration, as we saw I always find it fascinating, although I love watching the different shapes that fishes take depending on their environment. And so, we do have the funds in there. I can tell you, water in New Mexico, we call it sacred, we call it agua es vida. We know more than anybody else. We have learned how to live with water scarcity, but we cannot live without any water, right? We know how to live with water scarcity. We know how to protect it and honor it, but we must have water. And so that is the challenge of our day. And that is the challenge that I think, I am committed to. But I'll tell you what, I come to a conference like this, and I'm really excited about the work you're doing, but I don't know all the work you're doing, right? So I serve you, right? My office serves you. So if you have great ideas that you want us to think about and consider, if you think that there are funding opportunities, if you think that there are legislative changes that are needed, we're here, right? That's my job, is to listen to you, to take your ideas, to take your voices, and if we can get consensus around them, to turn it into funding, claims, accountability, legal, legislative changes. So remember, we're there for that. I want to introduce, I have amazing staff working for you. These are staff that work for the 3rd Congressional District. We have Derek Toledo. Would you please stand up, Derek? So this is Derek Toledo, and we have Loris Manuelito over here. So please reach out to us. As I said, we serve you, and we're here to hear from you. I will also say, for those of you who put in any grants, federal grants, if anything gets stuck, we are the WD-40 of the federal agencies. So, when things get stuck, we get out that WD-40, we can try to unstick them. If you are applying for grants, we can come and be your cheerleaders for those grants. So please reach out to my office, because water is life, agua es vida, and thank you for all that you do to preserve it. Muchísimas gracias. Thank you.
Thank you so much again, Congresswoman. We'll continue with our sort of improvised schedule. We'll now take a 10-minute break, and we'll reconvene here at about 10 to 3 with the remainder of our afternoon program. So stretch those legs, grab some coffee, tea, lemonade, or water, and we'll begin presentations again at 2:50. Thank you. All right, everyone. We can all start making our way back to our seats. We have a few more wonderful presentations to get to before we adjourn our conference for the 2022 Animas and San Juan Watersheds Conference. So I'm very delighted to introduce the first of two co-presentation that will be happening for right now. Lucy Parham is an environmental scientist at the Utah Department of Environmental Quality, Division of Water Quality. Her focus is working with EPA and other states and tribes in the San Juan River watershed to develop collaborative monitoring plans, conduct research to help inform watershed management decisions, and communicate the conditions of the watershed to stakeholders. She also manages watershed implementation projects in the Oneida Basin and develops total maximum daily loads, TMDLs, for the Jordan River. Prior to working for the Division of Water Quality, she was a water resources consultant in Salt Lake City, where she managed study design, data collection, analysis, and reporting for multiple watershed studies in Utah and Wyoming. She received her Master of Science degree in Water Resources from the University of New Hampshire in 2012. Thank you so much, Lucy, for joining us today.
Right. So thanks, Mark. So like Mark said, Shelley and I are going to be giving a joint presentation today on multi-jurisdictional efforts using Wind Act appropriations in the San Juan watershed. So post Gold King Mine, Congress appropriated $4 million per year for 5 years, so 2017 to 2021 roughly, under the Water Infrastructure Improvement for the Nation Act, or WIN Act. And a few other folks have kind of referred to their projects being funded under this act. And so this is what they were referring to. So basically this resulted in a collaborative effort from all the entities that were impacted by the spill. So Utah, Navajo Nation, Ute Mountain Ute, New Mexico, Southern Ute, Colorado, and Arizona. So we all, got together in collaboration with EPA to, determine the best way to spend these funds to better understand the watershed and also to improve water quality. So the framework that we operated under is shown in the diagram on the right there. And it consisted of 4 primary components: monitoring, assessing, informing, and acting. We're not going to talk about all of those components for this presentation, but I think it's important to kind of understand that this is what was sort of driving us through this process. So the first thing I wanted to touch on was some of the monitoring that's been going on. Shelley's going to talk about kind of where we're headed with the monitoring, but I thought it was important to give some context about where we've been and what we have been doing with regard to monitoring. So, post-spill, EPA, along, with other states and tribes, engaged in a watershed-wide monitoring effort. So the map on the right there is just showing where our locations, sampling locations were. So 39 locations all the way up from, Cement Creek down through the San Juan. We were sampling for a variety of parameters, metals, sediment, nutrients, and a variety of other things. The focus, though, initially has been really heavy on metals. So that's kind of a lot of what, the rest of my presentation will focus on. So the questions on the left, those were our questions that we were hoping to answer with this data that was being collected. And admittedly, it's a pretty ambitious list. However, we did make some pretty good headway in answering a lot of these questions. And I'm not going to go through all of them. I'm just kind of going to give an example from one of the primary questions that we focused on. But I do want to mention that, we all work together to kind of come up with this monitoring plan. And then Kate Sullivan, who's a scientist with the EPA, she was responsible for doing all of the data analysis. So the next few slides are kind of summarizing some of the work she did. EPA has a San Juan watershed website that is just full of much more detail on a lot of the stuff that Shelley and I are going to be talking about. We're kind of giving a surface level view, but it's 5 years worth of work. So a lot has been happening. So I encourage you to check out that website. So yeah, the first thing I just wanted to talk about was this initial question that we wanted to answer. What is the extent of water supporting state and tribal designated uses throughout the San Juan watershed? So in other words, if we go out and take a grab sample and look at the water quality, is it meeting the appropriate water quality criteria that supports, whatever we're using the water for, whether it's recreation or drinking water or agriculture. And so it seems like a relatively easy question to answer. However, when you're working in a multi-jurisdictional setting, things get, much more complex. And so one of the first sort of eye openers for us is, well, each state and tribe has different water quality criteria that they use to make these assessments. And so the table here, you're not meant to actually be able to see the numbers. I'm just trying to illustrate the complexity of, we all assess it a different way in some cases. And so that in and of itself is somewhat problematic. And, there have been ongoing conversations about trying to figure out a way to standardize these criteria moving forward. But that in and of itself is going to be a pretty complex process. So for the time being, Kate Sullivan came up with a way, what she calls a water quality index, that kind of normalizes these criteria and lets us look at the condition of the watershed on a more holistic basis. So I just wanted to show a couple examples of what she developed. And again, so this is looking at all metals for all uses across, all these jurisdictions. So it's very much a kind of a summary look at watershed condition. So you can see from the graphs here that, all beneficial uses have some exceedance of the water quality criteria at some time. So she found the overall exceedance rate was 3%. And then that bar graph is showing kind of by the use of the water, what those exceedances look like. So, the aquatic chronic use was the one that was exceeded most frequently. And then we took a look at, okay, well, when are these exceedances most likely to occur? Well, they occur during, all flows, but we tend to see higher exceedances during higher flows, which kind of makes sense. So this graph here is showing on the right there is showing what those exceedances look like under different flow regimes. And so there was a rain event that happened in March where we saw some of the highest exceedances by use. And then just to dig a little deeper, we looked at, well, what metals are most problematic? And found that, aluminum, iron, manganese, lead, and chromium. But again, this is watershed wide. I know we've heard from some other presentations that, when you start digging into certain sections of the watershed, then, that this narrative changes. But at least from a watershed wide perspective, these were some of the metals that we were seeing that contributed the most to water quality exceedances. So that's kind of the monitoring component. Like I said, there's much more information on the EPA website. The next thing I wanted to touch on is, so we had, all this monitoring going on, but in addition to that, each state and tribe was applying for funding to kind of conduct their own research projects within their own jurisdictions, or in some cases, watershed wide. We heard from Steve Austin and Jeb and Johanna about some of the work that they've been doing. Shelley's going to talk about some more of the New Mexico projects. So this slide is just meant to kind of illustrate there's a lot going on. Some of these projects have already been completed. Others are still in progress and will likely be for the next 2 to 3 years. So then I want to turn to, okay, well, what has Utah been focusing on specifically? There's a list of our projects on the left. We have, in addition to those 7, we have at least 3 others that haven't even gotten off the ground yet. So I'm not including them here. And then the map on the right is just showing the variation in spatial extent that each of these projects addresses. So we're, trying to get at, what's happening on the main stem of the San Juan versus, what's happening in Lake Powell, what's happening watershed wide. So various kind of spatial extents for these projects. So I'm going to talk about a few of them in a little more detail. The first one I wanted to mention was work that was done with the University of Utah, looking at source identification of metals throughout the watershed. After hearing the presentation that USGS and Navajo Nation are working on, they're doing a much finer kind of resolution of source tracking of metals. But this study was helpful for kind of giving more of a broader overview of what's happening and kind of where metals are coming from. But the main question that the author of this study was trying to answer is, can we differentiate, mining versus non-mining sources of metal in the watershed? And so she used cores that the USGS extracted in 2010 from the San Juan River Delta. And then she classified each tributary in the watershed as mined or unmined based on just, the number and types of mines in each of those watersheds. And then she looked at, she's got kind of different ways to try and tie, the layers in that core to a particular tributary, using both sediment characteristics, so particle size, shape, and density, as well as geochemical signatures, so enrichment ratios and lead isotopes. Again, the goal being we go back to this photo, you can see those nice layers in that sediment profile there. And so can we actually tie those back to a particular tributary? And she was able to some degree, using those techniques. Probably one of the more significant findings was that hydrology really determined which portion of the watershed was contributing the most metals at any time. So for instance, the Animas River was identified as a primary source of metals during snowmelt. Another way to look at this data is the bar graph on the right here. And this is something that Kate Sullivan came up with kind of based on the data from this study. And it's showing in that sediment core that was taken from the San Juan River Delta, the percentage of a particular metal and where it came from. So if we look at the lead bar, that's saying roughly 10% of the lead came from one of the mine tributaries. So this is somewhat interesting. However, you can see there's a lot of gray in the bars there, meaning, well, that's, it's the rest of the watershed. So there's still a lot left to be determined. And I think that's where, this USGS study is going to come in and really fill a lot of those data gaps for us. Then I also wanted to mention, this was probably our biggest study to date. It's a Lake Powell coring study. The goal of which was to collect sediment profiles in both the San Juan and Colorado River Delta of Lake Powell, and better understand metal deposition, the chronology of sedimentation, and rates of deposition, in the hopes that we could better understand impacts to water quality in both the San Juan and Lake Powell, particularly as Lake Powell levels get lower, some of that sediment becomes newly exposed. What does that mean for water quality? So in 2018, USGS spent about a month out on Lake Powell collecting these cores. We were able to get almost 40 cores. We collected from both deltas just for comparison. Generally speaking, Colorado they found to be had a thinner sediment water interface in the San Juan River, which wasn't all that surprising. And then these, so this graph here is showing the cores that were collected on the San Juan, in the San Juan River deltas. You can see there's a lot of variation in depth. So that's what the bars are showing, how deep these cores managed to go. The goal was to try and hit bedrock each time, which was not always possible. So you can see that there's quite a bit of variation. And then the photos on the right are just pictures of the different types of sediment that they found. Colorado compared to San Juan River. They were able to collect sediment from the historic, riverbed before construction of the dam. So that's the photo to the far right there of the cobbles and the, sandy deposits. And then they also estimated that, the Colorado is providing 44% of the sediment versus the San Juan, which provides around 29% of sediment to Lake Powell. So this study's ongoing. We're hoping to have it wrapped up by the end of the year. And ideally we'll get a few publications looking at, more in-depth sediment chemistry. We're also trying to find evidence of, the Gold King mine spill, which it's not looking like that is possible, but there's still a few more, there's still some more work to be done there. They have been able to find signals from some of the spill events that occurred back in the 1970s that were much larger. So be on the lookout for that. And then the last study I wanted to mention that we are doing is a watershed-wide E. coli analysis. So this project's kind of just getting off the ground. So Melissa and Alyssa, so they have been working on this for us. We really wanted to kind of take what they had done in New Mexico and expand it watershed wide. Because I mean, E. coli is just, at least in Utah, I mean, we're seeing more and more impairments every year. And so trying to get a handle on this, I think is really important. So at this point, they've compiled all the data. But moving forward, we want to look at sources of E. coli hotspots, data gaps, with the ultimate goal of being able to figure out where is it coming from and what can we do to address it. But now that they're leaving, we'll see what happens. So with that, Shelley, I'll hand it off to you.
Awesome.
Put my reading glasses on so I can actually see what I'm talking about. Thank you, Lucy. That was really great. So what I'm going to be doing is talking about some projects that we've been working on here in New Mexico, and then also talk about our multi-jurisdictional monitoring program that we are kicking off this year, actually kicking off next week. Woohoo! So I'll be talking about that and giving you a little bit more details. And some of these projects we've covered already, so I might gloss over some of them. But for the main focus in New Mexico, we've been looking at metals, we've been looking at E. coli and also nutrients. And then in the early projects, we looked at agricultural communications and outreach because that was the main impact right after the Gold King mine spill, was just getting that stigma of water in the San Juan Basin from the Animas and the San Juan River, and looking at the impacts on the agriculture and the farmers here in New Mexico. So the first 4 projects that are listed on this slide, the regional groundwater monitoring and surface water connectivity, the analysis of contaminants on attainment of livestock watering and irrigation uses, agricultural communications and outreach, and the Lake Farmington coring study, those are already done and completed. They've been presented, well, the Lake Farmington coring was presented earlier today. And the other 3 projects, I have more information on it if you're interested and want to learn what has already been presented at previous conferences, but I'm going to talk about the active projects that we have right now. So the first one, which also Jeb talked about earlier today, so I'm not going to get into too much detail because he had a whole presentation on it, but it's looking at real-time metals concentrations in the Animas and San Juan rivers and using that turbidity and suspended sediment to estimate those metals concentrations. Like Jeb mentioned earlier, it's a 3-year project and it kicked off last October. So they've been collecting data. We've had our planning and, it's in the initial stages of the project. So we are looking forward to getting some more information from that project. And the graphs on here are just representations. They're not actual data that we've collected. I wanted to find some sort of visual to show like what we're looking at doing and using different data to develop those correlations between suspended sediment and turbidity and metals concentrations in the rivers. The next project is another USGS project, and we're looking at nutrient sources in the watershed. Basically, we're trying to assess nutrient sources in the Animas River, and that will be used to build a watershed nutrient model that describes and predicts nutrient loading throughout the Animas River watershed. Basically, the USGS is going to conduct detailed geochemical analyses of groundwater, surface water, springs, seeps, alkali, and Cretaceous rock to identify and estimate relative watershed contributions of nutrients that cause eutrophic conditions, so algal blooms, and also exist in concentrations that lead to exceedances of the standards for drinking water. So New Mexico has groundwater quality standards for drinking water and also the EPA drinking water standards. So the USGS, the intent of this project is for the USGS to construct a watershed model that describes and predicts nutrient loading through the Animas River watershed by spatially analyzing land use, geology, and soil type, and climate data in conjunction with the nutrient geochemical sampling and analysis. This is also a 3-year project. It kicked off in October of 2020. COVID happened. It's still under progress. I'm not sure if it will need to be extended, but it's still a 3-year project. It's ongoing. And we've done, well, I will say the USGS has done the planning and training, field work, and has started model construction and calibration. So that project is ongoing, and we should be able to update again next year. And then our third active project that we have ongoing right now is implementation of the Lower Animas River Watershed-Based Plan. And that plan was accepted by EPA in August of 2016. So a watershed-based plan identifies pollutants of concern, identifies the loading reductions that are needed in order to meet standards, and also identifies some potential projects or best management practices that could be implemented to help reduce those pollutants from going into the river. So this project is implementing those restoration projects to help reduce certain pollutants. Turbidity is a focus, nutrients, total phosphorus, temperature, and dissolved lead. That will, hopefully those pollutants will be reduced by the projects that are implemented. And so it will help our cool water aquatic life designated use to be met, because right now those pollutants are at higher levels than what are needed in order to attain that aquatic life use. So management measures under this plan will include a soil health outreach campaign, bank stabilization and restoration measures, wetlands restoration, a riparian garden installation, and broader outreach and coordination with stakeholders. Right now, the implementation projects are ongoing and include construction surveys, project designs, and project implementation. We're also working with stakeholders and conducting workshops and meetings, and developing project plans and consultation reports. And like my presentation from yesterday about the River Stewardship Program, we do have more information, like very specific project information at the link. It's also available on our website. So the link is there if you are interested. All right, so now I'm gonna shift gears and talk about our multi-jurisdictional monitoring program. And this program is in coordination with the jurisdictions that were impacted by the Gold King mine spill. So right now, the states and tribes that are involved in this monitoring program are the Colorado Department of Public Health and Environment, the Southern Ute Indian Tribe, the New Mexico Environment Department, Navajo Nation, the Ute Mountain Ute Tribe, and Utah Department of Environmental Quality. So Lucy touched on this already, but I'm gonna give a little bit of background. The data that Lucy provided and showed in the first part of her presentation was the EPA-led monitoring program, which was in existence from 2016 to 2021. It was a program that was designed for the long-term monitoring program that was developed after the Gold King mine spill. And basically EPA implemented it because they had the resources to kind of get it kickstarted. There were 39 sites in the Animas River, the San Juan River, and then selected tributaries, and basically metals and nutrients, and then the physicochemical grab sampling data like temperature, dissolved oxygen, specific conductants were collected. Those were collected 4 times a year, and my circles don't really show very well, but it was base flow conditions, and then winter low flow conditions, the rising limb of the runoff and then trying to get the peak runoff. So there were 4 different sampling events, and EPA also collected biological data to help with the interpretation of the chemical data. All of this data is in EPA's database WQX and available on the data portal. Actually, New Mexico used the data from these studies in our 2020 integrated list, and we pull data all the time from that for our biennial listing. So our jurisdiction-led monitoring program, with the conclusion of the EPA-led sampling plan, we needed to develop a new cooperative and coordinated monitoring plan. And this plan leverages the individual strengths of each jurisdictional program to provide a better geographic and temporal coverage of monitoring. So the objectives are really pretty easy, provide monitoring data at a frequency greater than what we can typically provide. So for example, the New Mexico Environment Department, our monitoring team is on a rotational basis. And so we sample watersheds on a rotating basis. Essentially, we get to a watershed once every 8 to 10 years. So that's a pretty long time to have in between monitoring. This program will hopefully decrease that, and we'll have data from this watershed every year. We also want to establish a consistent collection schedule, parameters, methodologies, and analytical regimes across the jurisdictions so that we can compare data, and we're comparing apples and apples instead of apples to oranges. So that was the other objective. And like I mentioned, we're starting next week. So that's super exciting, our first sampling event. This is a map of the sites, and it's kind of a subset of what EPA was using. EPA had 39 sites. We focused in and prioritized 13 sites. And we are looking at those sites going from the headwaters all the way down to almost Lake Powell, but into Utah. And again, our sampling location, our sampling frequency is a little bit reduced. We're going to sample 3 times in a year. So we're looking at summer base flow, the winter low flow, and then runoff. So our sampling next week is runoff, even though we're a little bit late because runoff happened earlier than we thought. So it's probably on the descending limb of that runoff. Just to give you an idea of how we're going to pull this off, we're, like we said, we're collaborating, we're doing different things, and depending on the strengths of each jurisdiction and the capacity of each jurisdiction, we took on different responsibilities for this monitoring. So in the upper watershed, in the Colorado portion, Colorado is actually going to do both the sampling and analysis of their samples. In the middle part, from Southern Ute down to Farmington, the Southern Ute Indian tribe is going to sample, and the New Mexico Environment Department is going to provide the analytical services for that sampling. And then in the rest of the downstream portion, we have a combination. Navajo Nation is going to be sampling those sites, and the New Mexico Environment Department and Utah Department of Environmental Quality will be providing the analytical services. So it's really a collaborative event. We are going to be sharing the data and providing the data across the jurisdiction to help with that comparison and looking at those watershed-wide assessments. And so for this first year, because we're kicking this program off, we're looking at several different parameters. We're going to be analyzing for metals, both total and dissolved. We're looking at nutrients and then minerals and also E. coli bacteria. That's pretty much a pollutant that's prominent throughout the whole, the whole watershed, I believe. And we'll be collecting grab data, temperature, pH, dissolved oxygen, et cetera. And Colorado is currently the only jurisdiction that is going to be collecting sediment. That may come in later as we develop this program a little bit more and figure out what our capacities are and see where we meet, what other questions come about from this sampling event. But currently, we're looking at grab samples, and we're also excluding specialized collection techniques just because, again, like that may come in later. But right now we wanted to start off with a baseline to see where we're at and then grow from there. So what do we do with the data? This data will be uploaded to WQX. Again, it's jurisdictional data. Our state data typically goes up to the water quality portal. So it'll be available for anyone who wants to use it. And hopefully, at a minimum, the tribes will develop their assessment reports using this data, and states will use the data. Like I said, at least for New Mexico, we're already doing this to develop our integrated reports and list of assessed surface waters. And the goal is to provide that watershed-wide assessment. And that was that very complicated table that Lucy had shown, getting that more refined and more detailed, maybe not more detailed, more refined to give us a better idea of what's happening throughout the watershed and looking at those trends. So with that, I will leave it up to questions. I have the contacts for each jurisdiction up here for the states and tribes. So thank you. And we'll both answer questions. So if you have any questions, please let us know.
Maybe just continue on with emergency. Last, just kind of summarized. The importance of the WIN Act to be able to classify the momentum, migration. So without the WIN Act, know how we can continue this momentum so we can better help prepare people and address urgent issues. What's the next post WIN Act? What's the next? What we can do to continue this work?
And that's a very good question. We are always looking for opportunities to fund, because we definitely agree, like that's why we do what we do, because water is important, especially water in this environment is important to everyone who lives here. We understand the critical nature of having a good supply of water that will help us continue in this area, enhance and grow our society. With the discontinuation of the WIN Act funding, that's part of this project, is capitalizing on the strengths and resources of these state and tribal governments to help continue the program. And hopefully, as we move forward, we'll be adding things, like I said, the intent is to start this and see where we're at and reassess each year as we move forward. But we do have a commitment to this watershed, to water in general, especially for me in New Mexico. My program is for the whole state of New Mexico. This area is very specific and special. So it's looking for those funding opportunities. I'm not sure if we're going to get additional funding from EPA. We do have some bipartisan infrastructure law funding that is coming into the state that might be able to be used in different realms that we talked about at this conference already, to help with efficiencies in water infrastructure, to repair infrastructure that might be broken, to help with restoration and things like that. So we also have other programs like I talked about yesterday, the River Stewardship Program that is bringing in, it's a one-time boost of funding. It's going to last for 3 years, 4 years. So, as we move forward, hopefully we'll get more publicity on the need for more investment. investment in water is critical, and we try to make that argument every day. Not only, I think citizens know about it, but to our leadership, to our congressmen, congresswomen, to our senators, to EPA. So an idea also might be to have, under the Clean Water Act, there are regional funding opportunities like the Great Lakes and Chesapeake Bay. I'm trying to figure out how to get this jurisdiction, the greater San Juan watershed, as part of those special areas that could be funded under the Clean Water Act. That doesn't mean that we'll get funding every year, because, you know, the last couple years, Great Lakes didn't get it. Chesapeake Bay got less money. So, but it's something to show that focus and that importance of those different, this watershed in particular. Do you have anything to add?
No, I mean, I think you pretty much covered it. I guess the only thing I would add, and I really appreciate that comment, is, yeah, I mean, the relationships that were formed during this process are, I mean, that's the bedrock for carrying this forward. So that in and of itself has been hugely valuable for this effort. And I mean, as we continue to stay in touch and we collaborate on the monitoring, I mean, we already have ideas for, there's a program with NRCS, PL 566, that has the potential to bring a lot of funding to the watershed. So the idea is just to keep brainstorming and coming up with these, sources of funding that allow us to address water quality issues at the watershed scale. So.
I think we have to continue on with the rest of the we have to get up with the rest of our program, but Lucy and Shelley will be available for any additional questions following the presentation. So I want to make sure we have enough time for our final presentation. Okay, thank you. Thank you so much, Lucy and Shelley. All right, let me see here. Oh, escape. Never mind. Okay. All right, well, I'm pleased to introduce our final presenter of the 2022 conference, Maggie Hart-Stebbins. In December of 2019, Governor Michelle Lujan Grisham appointed Maggie Hart-Stebbins to serve as New Mexico's Natural Resources Trustee, a role in which she's responsible for ensuring that our state's natural resources are restored and communities made whole following contamination by hazardous substances or oil. Her appointment as trustee followed more than 10 years as a Bernalillo County Commissioner, where she championed environmental initiatives such as cleanup of the bulk fuels facility groundwater contamination at Kirtland Air Force Base, reducing nitrate contamination on waste from on-site wastewater systems, energy efficiency, and preservation of open space. Thank you so much, Maggie.
Thank you. Good afternoon. My name is Maggie Hart-Stebbins. I'm New Mexico's Natural Resources Trustee, and I want to start by just saying how delighted I am to be here. I love the work I do. I think the Natural Resources Trustee has a very important role in holding polluters accountable. So I want to say thank you to Shelley Lemon for extending this invitation, and to the Resources Institute for including us. So I realize we are behind schedule. I am going to try and just whip through this as quickly as possible, but I have my email address and contact information at the end of this. So hope you will contact me if there's anything I haven't covered or you have questions. So the Office of the Natural Resources Trustee. We are a very small state agency. We're located in Albuquerque. And currently there are just 3 of us. We have actually an opening for our executive director. So if any of you are interested in the work we do and want to come work with us in Albuquerque, we'll be posting that soon. We get really excellent legal representation from the New Mexico Attorney General's office. Bill Grantham is our legal counsel. So let's see, figure out next slide. I'm going to give a really quick overview. So our mission, I'm going to talk first about our mission, what our role is in the state's response to contamination. I'm going to talk about the natural resource damage assessment and restoration process. I will then go to the specifics of the Gold King mine release and the natural resources damage settlement with the mining defendants. And then I'll go to how we put together the natural resource restoration plan, and then conclude with what our next steps are. So that's my overview. So New Mexico's authority to pursue natural resource claims is really I would say often overlooked, and I think undervalued. But natural resource damages, it's an essential component of holding polluters accountable and making communities whole following the release of contamination. So when toxic substances pollute our resources, both state and federal law require a complete and timely cleanup to protect public health. And then those laws also require that natural resources be restored to the way they were pre-contamination, and compensation for lost natural resources and the services they provide. And you will see that I will come back to that services component later on in the presentation. Our authority is established by state law, the Natural Resources Trustee Act, and by CERCLA, also known as the Superfund Act, the Oil Pollution Act, and the Federal Water Pollution Control Act, or Clean Water Act. So how do we compare with what the Environment Department does? So following the release of hazardous substances, we share responsibility for the response with the Environment Department. So the New Mexico Environment Department is responsible for remediation. That's a cleanup to protect public health. So NMED's focus is on current and prospective risks to human health and the environment. Our role, we are responsible for restoration. So that is returning affected natural resources to their pre-contamination condition. And if that's not possible, replacing, acquiring equivalent resources. We also have the role of ensuring that communities are compensated for the loss of natural resources and the loss of use of those resources and the services they provide. So under the Superfund Act, there are federal regulations that were promulgated by the Department of the Interior for pursuing a natural resources claim. So we follow this process. This is not absolute, but should we have a claim that we take to litigation, following these specific steps will put us in a better position to be successful in court. So under CERCLA, we have these we follow this specific process, the natural resource damage assessment and restoration process. Our first responsibility is to assess the injury. So following the release of some contamination, we assess the impact of hazardous substances on natural resources. The next step is to determine damages. So when I say damages, that's the amount of compensation required to return natural resources to their original condition. And the measure of damages, and I'm just going to read from the DOI regs, the measure of damages is the cost of restoration, rehabilitation, replacement, and or acquisition of the equivalent of the natural resources to their baseline level of service. And so that damage assessment process, once we have quantified the injury, we look at what projects exist to restore the resources, and then we monetize the injury that way. The next step would be then to reach out to the responsible party, the potentially responsible party, and either try to reach a settlement on what the damages should be, or proceed to litigation, hopefully successful litigation that brings a certain amount of money to ONRT. So that's where we determine the damages. So once there's been a settlement or a recovery in court, we are responsible for preparing a restoration plan. So we work with local communities, with the affected communities to identify restoration projects that they would like to see. We we ask for proposals, we vet and evaluate the potential restoration actions, and then we put together a restoration plan. We put those projects into a draft restoration plan, which we publish for public comment, and we integrate public comment into a final restoration plan, which then becomes our roadmap. So how do we spend the money to restore natural resources? Then we implement, and generally ONRT will partner with local governments to implement these projects. So that's the process. So I'll talk about Gold King mine release now more specifically. I don't think anybody needs to be reminded about that from 2015. Certainly the visuals are quite memorable. So I think you all know Gold King mine release, an estimated 3 million gallons of acidic mine waste and almost 900,000 pounds of heavy metals flowed downstream into New Mexico. And you can see the bottom of that map. That is the area of our interest. That is the impact in the state of New Mexico. So in 2016, the state of New Mexico and the Navajo Nation filed lawsuits against the United States EPA, its contractors, mining companies for the environmental injuries resulting from the spill. In January 2021, the state reached an $11 million settlement with Sunnyside Gold Corporation and its parent companies. And that settlement included $1 million for my office, for ONRT, for restoration projects to address natural resource injuries. And important to note here, litigation against the US EPA and its contractors is ongoing. And I will get to that again later. Oops, sorry, I thought I'd taken the slide out before I'd gone over this. So with the $1 million that was recovered from the mining defendants, ONRT embarked on our process for developing a restoration plan. And I don't know if you can see all of these dates, but once we knew in January, once we knew that these settlement dollars were coming to ONRT, we began developing a list of stakeholders in the affected area. So that were communities along the Animas and San Juan rivers. We began working on establishing our criteria for selecting projects from the proposals we received. So January 15th of 2021, we sent a request out to sort of major media and all of the stakeholders we had identified at that point in time, asking for project ideas. We hosted a webinar so that we could answer questions if people weren't clear on our process or what we were doing. And then we had a deadline of September 14th of last year. Proposals were due. We then went through our screening and evaluation process. And by December 1st, we had come up with a draft restoration plan. So we had vetted all of the projects against the criteria we had established and come up with a restoration plan that included 4 projects. We then put that out for public comment, which is required by law. And by January 14th, 2022, we had all the public comment, we incorporated it into the plan and published the final plan last February. Since then, we've been drafting the memoranda of agreement with our project partners. And I'm hoping by the end of this month, the MOAs will be complete and projects can get underway. Part of our process, we had to identify what were the injuries, natural resource injuries caused by the Gold King mine spill. So I think this slide is important because ONRT does not collect any data on our own. So we work with the Environment Department, EPA, any other entities that are collecting data. And so we use that, outside data for all of the work that we do. These are the screening criteria. I think given the time, I'm not going to go through those, but screening criteria, those are the ones that we use to look at the projects, and it's just a baseline. Do they meet the requirements of the CERCLA process? And then we had a number of evaluation criteria that we used to rank the projects that met those initial screening criteria. And again, I think if you want, I'm happy to go through this, but a lot of detail here. So at the end of the process, when we published the final restoration plan, we funded 4 projects that will benefit the communities that were injured by the Gold King mine release. So we're working with San Juan County on a boat ramp on Animas. We're working with the city of Farmington on a farmers market pavilion at Gateway Park, working with the San Juan County Soil and Water Conservation District on a soil health project, and working with the Hogback Navajo community on a project to upgrade their irrigation system. So when you hear about natural resource injuries, often the thought is the money that goes to that money that's recovered through either settlement or litigation needs to go directly to benefit the resources. And that is often the case and a valid use for the money. There is also the element that says we can compensate communities for the loss of use. And so with the Gold King mine release, I think it's recognized that, you know, the agricultural community felt they either couldn't or didn't use the water. So these projects you'll see have a lot to do with working with the agricultural community to try and compensate for that loss. And then the outdoor recreation industry, again, suffered because of the international coverage of the bright yellow water flowing through the community, and, the impression, the stigma that this was no longer a safe place to be. So that was the intention of funding these projects, but it's also important to point out these were the only 4 that we received. So we were really the only 4 proposals we got. So we were really delighted that they kind of met our goals and that we had enough money to cover them all. So ongoing litigation, I think what I can say is that, and I have this very specific language from my lawyer, due to the ongoing work to finalize the settlement, all I can say is that New Mexico and the United States have jointly requested a stay in the litigation between them to finalize a settlement. So I think I'm optimistic that that will be successful and that there may be additional funding that becomes available to us to, again, do additional restoration. So my point there is, if you think that you either have a project or know of people who might have projects that would and would want to apply for this funding, that is an email address to which you should send your contact information. That will put you on our outreach list when we, number one, know that we have funding and we are in we are ready to start that outreach process again for whatever comes next. So I think that is all I have to say. So 2 things, keep us in mind if you think you want to work for a really dynamic operation in Albuquerque. We have both the executive director position open and a water resources professional 4 that will become available, will open up in July. And secondly, if you think you have projects, again, this is the target area. This is the area of impact. So if you have projects and want to be on our mailing list, please reach out to me. And that is it.
Questions for Maggie? Is there anything in the chat?
Excellent.
Thanks so much.
Thank you.
All right, well, thank you everyone who has stuck around till right now. I just want to, I guess I'll try to just say a few closing remarks, and then I'll open it up for any remarks from our conference planning committee members, just because by no means would I want to kind of speak for the kind of conference organizing process as a whole. So but I just want to take this chance to first of all thank all of our presenters, oral presenters, poster presenters who've been here through the past 2 days. It was really a pleasure to be able to help convene another Animas and San Juan Watersheds conference, and both to bring it back here to Farmington, New Mexico, but also to make an option available for those who couldn't join us live in person, but can nonetheless join virtually online. I do want to say that I look forward to keeping everyone who's participated or anyone who might want to either present or attend subsequent conferences, keep you all in the loop about next year's Animas and San Juan Watersheds conference. We'll be hosting these conferences at least through 2024, and from there we'll be exploring ways to continue to host this forum for updating and sharing information on the ongoing collaborations, research, monitoring, projects of all kinds that are happening here in the watersheds. I do want to give a big thank you to our conference planning committee for this year. Since the last Animas and San Juan Watersheds conference, we've had some new folks join the planning process, and we look forward to having them continue through subsequent conferences. But I want to give a big thank you to everyone, Steve Austin, Melissa Benfer, Johanna Blake, Carol Clower, Rob Cook, Anthony Edwards, Shelley Lemon, who you just heard shortly before, Kevin Lombard, Yesenia Lugo-Hams from the US EPA, Melissa May, Paul Montoya from the city of Farmington, Shira Reams from the EPA, Alyssa Richmond, and then as well the staff who helped from NMWRI, including Jeanette Torres, our program manager, Carolina Mijares, Animwery director, Sam Fernald. And then of course, I'd like to give a big thanks to the Animwery staff who were providing technical and coordination assistance here. Anik, Mary Beth, Jeanette, Marcus, and Kaustav. You all have done a wonderful job here. I think pretty sure for everyone else except me, it was their first attendance of this conference. So I'm glad you all got a chance to experience that. Like I said, I did want to provide a chance if there's any members of the conference planning committee who'd like to say a few words. Anyone who wants to step in the hot seat and share some thoughts on the watershed or the conference in general. I'll open it up if you'd like. Otherwise, while you're thinking, I'll at least just take a chance to, I want to, the conference also doesn't just end here. Technically, we do have a few post-conference events, but I do want to also say a big thank you to those who helped to organize our pre-conference Shiprock Sustainability Fair. Most notably, amongst those, I want to give a big thanks to Dr. Carletta Chief from the University of Arizona, Dr. Kevin Lombard of the New Mexico State University Agricultural Science Center at Farmington, as well as his staff who helped with that event, Brandon Francis, Corbin as well, who helped with that, as well as other partners from the University of New Mexico, Northern Arizona University, and those who were involved in the Intermountain West Transformation Network. A big shout out as well to our post-conference field trip organizers, including the Navajo Agricultural Products Industry, the Cooperative Extension Services for San Juan County, who will be hosting the self-guided tour of Growing Forward Farm tomorrow, and the Ag Science Center again, who will be helping to host the tour of their facilities and of the NAPI facilities as well. And of course, for our post-conference rafting trip on Saturday, Desert River Guides and the City of Farmington as well. Just want to, one last time, if there's any other conference planning members. Oh, Melissa May, thank you.
I just wanted to come up and give an extra round of applause to Mark for all the work he did organizing this. He was herding all of the cats, all of the busy scientists and agency professionals. Truly did an excellent job. Thank you for being our MC throughout the whole thing. And we're really lucky to have this quality of a conference in our little town. And so thank you to all the researchers, the agencies, everybody who's brought your expertise here. It's truly appreciated, and really thank you, Mark, and all the WRI staff. Everything has been fantastic. This has been a great conference.
All right, thank you so much, Melissa. Well, I don't have a gavel, but I guess that's I guess I can say that this year's 2022 Animas and San Juan Watersheds Conference is adjourned. Thank you.